Good evening, good evening, good evening. This is your Captain Shreyas on the PWJ English channel. Welcome aboard everyone. This is a very important class because current electricity is one of the important chapters, weightage wise, even number of questions wise, or even the level of questions wise. So not just for mains but also advanced, and every single examination that you will be giving, whether it is BitStat, whether it is ComEd-K or your local entrance test, you will see current electricity has a major chunk, right? So let's begin with this chapter, and let me know quickly if I'm audible and visible to all of you, because today you're going to learn concepts. You're going to see how to use these things into applications via some problem solving. Everything will start from the scratch in this particular session, and the entire concept of current electricity, the chapter, will be done. We'll be starting off with the concept of current, then current density, then drift speed, right, conductivity, resistivity, all these parameters. Then we will slowly move on to electrical power, Ohm's law, and then the theorems which are there: Kirchhoff's voltage law, Kirchhoff's current law, maximum power transfer theorem, the concept of EMF, and combination of resistors, combination of cells, and some complex circuits. That is the plan for this particular session, right? I hope you guys are ready. Hi Sundar, hi Josh, hi Unique, welcome everyone. And by the way, Shreyas Sir is working on something really cool and amazing for all of you, so that you can plan and prepare for your JEE, for your advanced, for any other entrance test with ease, so that you don't have to worry about your roadmap, your timetable, balancing boards and JEE together. All these problems will come to an end. So stay tuned on the channel, because Shreyas Sir is making something really helpful. I will make that video very soon. Okay, so be there on the channel so that you do not miss. Hi Devesh, welcome. Yes, I do remember you, man. Welcome aboard. Yeah, good evening, good evening. All right, so let's begin with this particular chapter of current electricity. Now, before this, whether you go through H.C. Verma, NCERT, Physics Galaxy, any book, what you have learned is electrostatics, meaning there are charges. Electro is related to charges. Statics means it is at rest, or their velocities, you are neglecting it. So you were studying fields, forces due to charges which were at rest, okay, or even if they were moving, you are not bothered about it as of now. Now slowly you are transitioning to electrodynamics. Electro again means charges, or something related to charges, and dynamics obviously means something related to motion. So now you will see the charges are in motion. The charges will be flowing. So in this particular chapter, what you're going to see is the charges will be in motion. Basically, it is obviously the next follow-up of electrostatics, the natural flow. When some things are at rest or stationary, next it will start moving, and that's what you're going to study. And that is nothing but the flow of charges, which comes under this chapter of current electricity. Okay, did you now get a perspective of this? Did you now really get a perspective about this particular concept? Yeah, okay. Question solving series, yes Sundar, I will definitely initiate a question solving series. Right now I am really held up, man, and a lot of kids are also held up in their coaching. Just give me some time, and I am trying to finish off as much as possible in my batches, and making sure I will be there only for all of you for your JEE. so that I can fully be devoted and focused. Right now I'm on 2 channels, so that is what it is. So once all these things are sorted, I'll make sure that I am only there for you and preparing you for JEE. Okay, so it will come very soon, don't worry. And then I will plan all these problem solving series, difficult problems, JEE Advanced questions, NSCP level questions. This is what I want to do now on, you know, for all of you. Anyways, now let's understand these concepts in detail, guys, because this will also help you for your semiconductors, which is the last chapter of physics class 12th. So whatever you understand here, you better understand it well, because you go into microscopic level in the last chapter of semiconductors. Now usually when you have a conductor, let's say this is our conductor. This is our conductor, and when I say conductor, it means like metals. We have discussed what a conductor is in the first chapter. You will notice that your electrons are moving randomly here and there, and you know, there is a random motion with collisions, speeds, directions, everything changing. So if you focus your attention on any random electron, you will see the path will look something like this. So this is the motion, looks like a Brownian motion of electrons. This is the motion of electrons. Obviously it is completely random. Now if you choose any cross section, doesn't really matter how, where, doesn't matter. You will notice for any such section, for any such cross section, whatever electrons are crossing from one side to the other, exactly that many number of electrons are crossing from this side to the first one on an average. So there is no net transition of electrons. So I will say there is no net flow of charges. There is no such flow of charges, and everything is, I would say, under static condition. The total conductor as such is neutral. There is no charge on the conductor. Yes, it is neutral. There are no charges on the periphery inside which are unbalanced. There is no, I would say, different concentrations of charges, like one side is more positive, one side is negative. No, it's a regular conductor, and this comes under the concept of your electrostatics, where you know the total charge on the conductor is 0. There are no surface charges right now, right? There is no extra charge given to it. The field inside is 0. Everything is more or less stationary. Everything is static. So I can also conclude this fact that there is no field inside. There is no electric field, to be more specific. There is no electric field. There is no electric field inside. There is no electric field inside the conductor. Not just that, there are no accumulation of charges. Nothing such is happening in over here. It's a regular conductor like you have studied in electrostatics. Agree with this pointer? Now things are going to change. Here, the main idea is there was no field. There is no field, there is no accumulation, there is no net flow, there is no flow of charges, there is no current. Yeah, so all of this says that there is no current. There is basically no current in this conductor, I would say, and current means flow of charges. Like I had said over here, flow of charges constitutes your current electricity. Now imagine the same conductor in a slightly different scenario. This is the same conductor, but what is different is one side is connected to positive terminal of a battery and the other side is connected to the negative terminal of the battery. Meaning If I have connected it to positive and negative terminals of a cell or a battery, meaning I have created a potential difference. Yes, so there is a potential difference which has been created. And whenever you have different potentials, whenever you have two regions of different voltages, potentials, what flows and from where to where will it flow? Voltage difference creates fields, and the fields always go from higher potential to lower potential, if you remember from the chapter of electrostatics. Yes or no? So what you will notice now is this side which is at a higher potential, whereas this side is at a lower potential. So there is a potential difference. So the electric field will flow from higher potential to the lower potential. So now you see these electrical field lines going inside the conductor. That is way different than this situation when there was no electric field inside the conductor. Electric field was 0, but now I am saying there is an electric field within the conductor, and I feel this is one of the most important differentiating factors from the earlier chapter. Electrostatics, charges were at rest, net field was 0 within the conductor, but in electrodynamics, which is your current electricity chapter, the field won't be 0 within the conductor. And that is the reason why, probably the charges are in motion. And yes, why not? Think about it. If there is a field and you have an electron over here, electron is a charge, that charge will experience force. That charge will experience force. Yes, sir, explain every chapter as based on JEE pattern based. Yes, Oriva, I am explaining from the point of JEE Mains plus Advanced only. I am not teaching any other CET level or board level. I am going full into detail because for boards I will not go into so much of detail. Okay. Now, this particular charge, this particular electron will experience a force, charge into field, but since it is negative, it's an electron, it will experience a force in the opposite direction. So this particular electron will definitely experience a force, like this. This will experience a force like this. So now you might be thinking, sir, will the electron move like this? No. It's not like that. Electron will still move randomly, but just that now it will slowly start moving more towards your left side. Notice how in this previous situation, this electron which was there, on an average, I will say that eventually it will come back to its original place, meaning the average displacement for a long time for a large set of electrons will be 0. That means I can also say the average velocity is 0 when the net field is 0 inside the conductor, like in regular electrostatics. But now that will not happen. It will not necessarily return back to its place after a long time for a sufficiently large sample. In fact, it will slowly start migration, and the migration is happening because of this force, which is coming because of this field, which is coming because of the battery, which is the potential difference. So you will not just see this electron, it is every other electron story. You will see most of these electrons will slowly have a preferred path, which is slowly migrating those electrons towards the other side. So now you can see that the average velocity is no longer 0, and the reason for that is because they are migrating, and this effect is called as drifting of electrons. they get drifted within the conductor towards the side of the force acting on them, which is opposite to the electric field. So this phenomena is called as drifting. This is called as drifting. And this average velocity is then called as the drift velocity. So this is then called the drift velocity. Drift velocity, my dear warriors, and drift velocity is the average velocity of electrons under the influence of potential difference within that conductor, under the influence of that potential difference within that conductor. So that is called as drift velocity, and the symbol for that is Vd. V for velocity, D for drift. Did you now understand? This migration phenomena is happening. Otherwise, those electrons were randomly moving and they were having no net displacement. And that is what I showed it to you over here also. That is what I showed it to you over here also. Net motion was not there. So average was 0. But now there is an average motion and they are drifting. And that drift is called as drift velocity. Now, one specific pointer which I want to mention over here is this. If you just ask me what is the speed of these electrons, then that is of the order of couple of thousands of meters per second. Yes, these speeds, I'm not talking about velocity, average velocity is obviously 0. But if I talk about the speeds, which is a scalar, which does not worry about direction, that is in typically 10 raised to 3 to 10 raised to 5 meters per second, depending on a lot of other things like temperature, material, and so many other things. So it is basically very huge. Think about it, 1000 to 1 lakh meters every second. That's how fast, that's how these electrons are moving. But in spite of that, their average velocity was 0 because they were coming back after so many collisions back to their same place. But when you turned on the electric field, the potential difference, they started migrating. You might be expecting, sir, they will migrate very quickly. Actually, no, their migrational velocity, their drift velocity is very, very less. The drift speed is actually very, very less, typically in few micrometers per second to few millimeters per second. That's how small their migration is. That's very, very low, guys. So even after thousands of collision in a second, they are barely migrating a micrometer, but they are migrating and slowly they are migrating. Now, the moment I discuss this, a lot of kids have this confusion and they immediately ask, sir, then if there is a wire and let's say this particular wire, I'm showing a big cross section, is connected to a bulb. Okay, this is the coil of a bulb. This is a more zoomed in version of it. So this is that wire like this, and maybe this is a part of that switch over here, and you turn on that switch and the circuit will get complete. This is that positive side. Similarly, you will have negative side of the battery and this circuit will get complete. Okay, just visualize this. This is your wire. So students have this doubt, sir, how is it that the electrons are going at micro to millimeters per second, and when you have a battery, a switch and all these things, how is it that the moment I turn on the switch, within no time delay, the bulb turns on? Shouldn't these electrons take a lot of time to reach here? Say from here, there is one electron like this. Shouldn't this electron take so many minutes or hours to reach over here so that the bulb understands, oh, okay, there is an electron coming within me which is flowing. I have current. Let me turn on and let me start glowing. No, that is not what happens even if the drift speed is so less. What do you think is the reason for this? The reason for that, somebody will say, no sir, electron speeds are less, but sorry, electron drift speed is less, but the speed of the electron is very high, no sir. So I feel, sir, one electron will be there, it will escape and it will go inside the bulb and it will tell the bulb, listen, 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 current is coming, you turn on, turn on, turn on, and that's how the bulb turns on. No bro, that's not what happens. No electron will escape like that and it will go and tell the bulb, listen, listen, somebody is coming. Nothing like that happens, because these electrons, even if they have very high speed, they can't move much height. They are just going like this, like this, like this, like this. After hours and hours, they will reach here. After many hours, it will reach here. After more hours, it will reach here. More hours, it will reach here. After many more hours, it will reach here. It takes a long time for them to reach the bulb. The only reason why this happens is because it is the electric field which travels at the speed of light. And that's really quick, which is 3 lakh kilometers per second. Insanely huge. So yes, the electrons are still, drifting, migrating. They're slow process. This is very, very slow, but it is the field which carries that information. It is that field which carries that information. The field travels at 3 into 10 to the power 8 meters per second, which is basically the speed of light. The speed of light. And that, my dear friend, that is very quick. And that's how the bulb knows I have to turn on. So, in this process of this field being set up, all the electrons now know that, okay, the switch has been turned on, and that's how all the electrons in that wire begin to move almost instantly. So it does not wait for this electron to reach here and tell the next electron, hey, you need to move. This to reach here, hey, you need to move. No. The field sets up instantly almost, because this speed is insanely large, and that's why, in fact, all the electrons within this conductor begin to move. So this electron will also begin to move. So even this electron will also begin to move like this. It will start migrating. All the electrons everywhere will begin to migrate. Is this now conceptually very clear? So there are 3 speeds. Speeds of the electrons which are very large. Drift speeds which are very, very small. Takes the physical, you can say, migration of these electrons, which happens very slowly, versus the field which happens really quick. It travels at the speed of light. Okay, everyone? Awesome. Awesome. Yeah. Yes, Keshav, whatever your doubt is, let me know. But I hope it is related to the chapter. The notes of electric fields and charges, if it is not uploaded, I will just upload it. But I think it should be uploaded in the app, if I'm not wrong. But if it is not, I will ask the backend team, man. Okay, don't worry. All right, Unique Soul, I will ask the team to upload it. Don't worry, don't worry, don't worry. Great, sir. Now I understood all these speeds and how information is traveling within the conductor. It is the field which is carrying the information, and it is waking up. Electron, wake up, wake up, wake up, wake up, wake up, wake up. And it is waking up all the electrons in that wire. That is what it is doing. All right, great. So now let's start defining a lot of terms now that we understand what is really happening in this. Now you need to also know one more thing. So if you have a conductor, if this is our conductor, and within the conductor there is a electric field. I know you are wondering, sir, how much is that electric field? Don't worry, I will give you the answer in a bit. There is an electric field. That electric field will obviously go from high voltage to low voltage, from high potential to low potential. All right, high to low potential. The electrons average velocity is this way. This is the electrons drift velocity, which is exactly opposite to the field. But when I define current flowing in that wire, current is assumed as the flow of the positive sign of the or the positive movement of the charges. So if I tell that I have got some goodness in me, that means I have become a better person. If I say badness has gone out of me, still I have become a better person. So same way, if negativity is going this way, it is the same as saying positivity is coming towards the other side, exactly opposite. So that is the reason why we say that the current is flowing exactly in the direction of the field or exactly opposite to the drift velocity. So this is the direction of the current. Direction of current, electric current. It is always assumed as the flow of positivity. Positivity. This is the flow of positivity in sense of charges. Okay. So keep these things in mind. This is a conventional direction. Now, why is it positive? Why is it not negative? It's not got anything to do with motivation or demotivation. Sir, positive is better, negative is bad. Nothing like that. People in those times did not know why current flows. So they just assumed one particular direction, high to low voltage electric field is going, and yes, that is the direction of current. Later on, when Thomson discovered electrons and then they understood it's the electrons which cause current electricity, then they understood, oh, I have taken the current here, but actually the negative charges go in the opposite way. But by that time, it was so late to change the direction of the current, because already we had assumed the current goes from positive to negative. So changing the material, the textbooks and theory would be a painful process. So that's why we still use the conventional direction of current for historical reasons, nothing else. Now let's define electric current. Let's define electric current. You have a conductor. You have a conductor like this. This is part of the conductor. You take any cross section within the conductor. This is some cross section within that conductor. There will be some amount of charges which will cross, this particular section. Okay, these are basically charges which are flowing. It could be positive, negative, but we will always assume positive charges. Charges flowing and crossing that particular section within that conductor. So if you measure how much charge has flown or crossed a section in a unit time, that will give me the value of the current. So electric current is how much charge flows, upon how much time is basically taken. So the symbol for current we all know is I, the charge which flows is Q, and the time taken is basically T. Now this is usually the average value of the current. This is basically the average value of the current. But if I want instantaneous current, then I should use derivative symbol. It should be dq by dt. So in a small dt interval of time, dq charge has crossed that section. So at that moment, the current is I. That is how I will define it. Alright. So this is current. Yep. Now please remember, current is a fundamental quantity. It is a fundamental quantity. It is not derived. It is a fundamental quantity. The dimensional formula is just ampere. In fact, an ampere is going to define a charge, because a charge will be current multiplied by time. Okay, that's how the dimensional formula of charge comes from current, because current is fundamental, charge is not. That's how it is. The SI unit of current is an ampere, and an ampere of current is when a coulomb of charge flows in a second of time. Now usually ampere is a big unit. the most likely values of currents will be in milliamperes, sometimes even in microamperes. So that is the usual ranges of current. So what happens to the current and voltage during short circuit? We are going to discuss that, Manas. There are 4 different types of circuits I am going to teach you. Out of that, one of them will be a short circuit. I will help you with that. Okay. Sir, should I search for electric fields and charges nodes? Just search if you can get it. If it is not, then I will upload it. Okay. Sir, will the electron oscillating about the system and performing SHM when it will have electric field? It's not necessarily SHM because the forces are not proportional to the displacement. But yes, it will be a random motion. It is not an oscillatory motion. It's not like it will go back and forth oscillating, because there are so many other things in play over here. It is not a spring-like force. Is that okay? All right. I hope ellipse everyone has understood. Hi Mansa, everyone. All right. Great, great, great. Now, if I want to find how many actual electrons cross a particular section, let's say an example, in a current of 3.2 milliampere, how many electrons cross per unit time? That is the question. How many electrons are going to cross literally per unit time? So visualize this. You have a wire, and I am saying that, listen bro, there are some electrons which are crossing a section per unit time, and I tell you the value of the current also. This is our section over here. So I want to know how many electrons are crossing. Each electron will have a charge of E. So let's assume n number of electrons having each charge magnitude of E are crossing in a time of t. By definition, current is how much charge will flow per unit time. So if I have n number of electrons, each having charge E, the total charge which will cross will be n multiplied by E, and this divided by t as it is. So if you take this value of E on the other side, so you will notice n by t will be, current is on the top, E will come below over here. That's it. This is exactly what I wanted. How many electrons are crossing per unit time? So this is exactly number of electrons which cross per unit time. This is exactly what was asked. Current is 3.2 milli is 10 to the power minus 3 amperes SI unit. Electron charge is 1.6 into 10 to the power minus 19, of course. 3.2 by 1.6, that is 2. And then minus 19 goes on the top as plus 19. 19 minus 3 is 16. So 10 to the power 16. That's insanely huge amount. Yeah. 2 into 10 to the power 16. We should probably be talking in moles now. We are approaching that orders of number. Yeah. So a huge quantity, a bulk of electrons are crossing even for a mediocre current of, a small current of just 3.2 milliamperes. Getting the sense of it, right? Let's do the next question coming up on your screen, and here it is. A charge of Q rotates with angular speed of, okay, it is rotating with an angular speed of, let's say, omega in a radius of, or basically I would say in a circular path, find the current of the loop. Find the current of that particular loop. That is the question. Let's understand what it means. Imagine this is our circular path. It is not a actual wire or anything. It is not a physical entity. It's just an imaginary path which I have drawn over here, which is in the form of a circle. You have some charge which is q, and it is going around this with an angular velocity of omega. So I feel if a charge will keep flowing very fast, it feels to me like a loop. Loop means a closed path. So it feels to me like a loop of a wire carrying current. So this diagram feels like as if there is a loop, and that loop is carrying some amount of current. All right. I hope this is absolutely clear. It feels like that. So question is, how much is that equivalent current in that loop for this charge rotating with angular speed? So here is what we will do. Again, visualize a cross section, and for that particular section, my dear warriors, think how much charge will flow in how much time. So the answer for that will be, if I take that charge q, that charge q will cross exactly once in a single time period. So this charge will cross exactly once in a single time period. If I take the charge flowing to be 2q, that means once and twice, then the time taken will be 2t. If I wait for 3 time periods, the charge will flow 3 times. So the charge crossing it is 3q, but the time will also be 3t. So q by t is the simple ratio. If you want, you can multiply by 2, or multiply by 3, multiply by 3. It doesn't matter. Anyways, it will get cancelled. So the simplest fraction will be obviously q by t. And now the time period is 2 pi by omega. That is a standard formula for circular motion. If you remember, omega used to be 2 pi divided by time period. Therefore, time period is 2 pi divided by angular speed. Oh, perfect. So instead of time period, I can just put 2 pi by omega. Hence, the value of the current will be q omega divided by 2 pi. That is the answer. So this is the equivalent current of the charge rotating with angular speed omega. Thank you so much, Unique Soul, for all the love from Andhra Pradesh. Miruella Naru, Boundi. Yes. Thank you so much, man. Thank you so much. Awesome. Awesome. Like cheyandi, subscribe cheyandi, right? From all the Andhra students. I want that. Thank you for the love. Okay. Fine, Anita. Definitely considered, man. For now, I am here. Please keep learning. Okay. So, wherever I am, you should learn. All right. Now, next question. Simple. If I tell you the charge, let's say some random function is given. Let's say the charge is given to be t cube minus 2t plus 4, or let's say 2t minus 6t plus 4 coulombs. Find current at t is equal to 2 seconds. Let's say this is the question. All right. Now this kind of question also has come many times, so that's why I'm doing this. So current has to be found if charge is a function of time in coulombs. So we all know current is the derivative of charge. So instantaneous current will be nothing but dq by dt. So just take the derivative of this entire term, which is t cube minus 6t plus 4. T cube's derivative is 3t square minus 6t. So just minus 6. 4 is a constant. So the derivative will be 0. So basically it is 3t square minus 6. That is the value of the current. But the question is at 2 seconds. So that means the current at 2 seconds, substitute the value of time as 2 in this expression. So it will become 3 into 4 minus 6. 3 4s are 12. So it will just become 6 amperes is the instantaneous value of the current at 2 seconds. Yeah, very simple. Great. Now, if I change a small part of that question and instead of saying at 2 seconds, I mention find current in first 2 seconds. That's a whole different problem altogether. It's going to matter a lot, and that's where traps are being laid by your JEE. Okay, if you misread it, gone, doomed. At 2 seconds is that instant. But first 2 seconds, it's a period. And what do you think? Can I use derivatives now? Yes or no? Answer in the chat box. Can I use derivatives? Answer in the chat box. 1 second. No, right? Because it's a period and it's not an instant. And when there is a period, obviously, it's an average value, right? So basically, the question is all about finding the current in the first 2 seconds, meaning what is the average current in that period? Average current in that period of 2 seconds. That's a whole different problem. So then I know the time period is 2 seconds. And in that duration, how much charge has flown? That is what I will need. So that's a simple problem to do actually. What I will do now is I will say what is the charge at t is equal to 0 seconds. At t is equal to 0 seconds, charge is 0 cube minus 6 multiplied by 0 plus 4, which is basically 4 coulombs. Now, at t is equal to 2 seconds, how much charge has flown? Well, that will be 2 cube minus 6 into 2 plus 4. 2 cube is 8 minus 12 plus 4. So 8 plus 4 is 12. 12 minus 12 is 0. Oh, interesting. 0 coulombs. Great. So that means the charge which has flown is how much? 4 minus 0 or 0 minus 4, magnitude wise it is just 4 coulombs. Agree or disagree? It is just 4 coulombs. This is 4 and this is 0. So 4 and 0, the difference is 4. If this was 4, this was 1, the difference will be 3, right? So that's what I can notice. So what do I do now? Oh, great, Sally's. So now this session is going to be useful. Mithul, no need of integration, man. No need of integration. That's a whole different problem. Once I know this, finding the average current will be simpler. So instead of dq by dt, now it is delta q by delta t. That's what you should understand, which is how much charge has flown in that particular time period. So the charge flown is 4, time is 2. So hence it is 2 amperes. So the average current was 2, whereas you can see in the previous question when instantaneous was asked, it was 6 amperes. So yes, the current is growing, but in that period the average current was 2 amperes. So you should understand that before the current was very less, slowly it has piled up and increased. So the average has come out to be obviously lesser than 6, which sounds very reasonable. Understood? Okay, awesome. Meena Jaiswal, because I joined PW very, I won't say late or anything, but I joined after the batches had started and already, the teachers are being decided. So right now in the JEE English batches, I am not there, but I am teaching in another channel's batches as of now because those batches had started later on. So when the next batch will come, definitely I will be there. Okay, so don't worry about it. Maybe maybe the crash batch, maybe the next year's batch, whatever it will come. So that's when I will be involved. Okay, so for now I'm teaching on YouTube, and in the paid batches obviously you have the best teachers, so don't worry about it. Okay, now somebody said, sir, we need to do integration. Where that integration comes? It's in this kind of question. is the exact reverse question. Instead of charge, current is given, and from current you have to find charge. So for example, if current is, let's say, T square amperes, find the charge that flows in the first 3 seconds. That is the question. Now in this kind of question, obviously you will need integration. And how? Look at it. Current is dq by dt. Current is given, charge is asked. So obviously take dt on the other side, multiply it with the current. So dq will be the current multiplied by that small time interval. Now obviously we can put the integration symbol. dq will be integral I dt from whatever that time, and this is 0 to whatever is that total charge. So the integration of this will be q minus 0, and here what will I put? Put the limits. I started from 0 seconds till 3 seconds. The value of current is t square. So substitute that, correct? So q minus 0 is obviously q. T square's integration is t cube by 3. Limits still not put, 0 to 3. So that will be nothing but, first put the value of time as 3, cube it, then put the value of time as 0, cube it, divide by 3. So 3 cube by 3 is nothing but 3 square, and this is 0. So that is nothing but 9 coulombs. So the charge which flows is 9 coulombs. Clear? Alright. Amazing, amazing. Awesome, awesome. Yes, 9 coulombs. So understand when derivatives comes, understand when integration comes, and understand when derivatives nor integration will come, which is exactly this problem. So you need to adapt. I have done all kinds of models of question, including the loop problems, as well as finding the number of charges which flow per unit time. So now let's move to the next part, and that is current density. We saw what is current. Now let's see what is current's density. Current density. Imagine this cross section of a conductor. Imagine this cross section of a conductor, something like this. Yes, the electrons will move exactly opposite to the direction of the field, and current moves in the direction of the field. So let's say these are something like the streamlines of the current. So more charges go, more current streamlines, you can visualize it like that. The streamlines of current is like how, you know, those imaginary hypothetical paths which are taken by the electrons, but in the opposite direction, because the electrons will go like this, current will go in the exact opposite direction. So if an electron has traveled like this, the streamline of the current will be exactly like that. So how much of that current streamlines is there per unit cross section, of that conductor? That is what the density of the current is. So if I assume this area to be A, then the current density is defined as how much current flows through that section upon that cross section. So in this case, it is nothing but simply the current which is flowing per unit area. Now the symbol for this current density, my dear warriors, is J, and that J will be current divided by area. Simple definition. Now if you look at the unit of current density, this is amperes, this is meter square. So the SI unit will be ampere per meter square. Okay, don't get confused between these two things. So this is ampere per meter square. Dimensionally it is obviously ampere is a raised to 1, meter square means L raised to 2, but is in the denominator, so negative power of 2. So that's the dimensional formula. One more thing, it's a vector quantity. That's a strange thing. It's a vector quantity, and this vector is having the same direction, as of the current, That is a very important thing. Remember, current was a scalar quantity even though it had direction. Yes, even though it had direction, it was a scalar quantity. It was a scalar quantity even though it had direction, because it doesn't obey rules of vector addition, doesn't obey vector rules. So unfortunately, it had to be classified as a scalar quantity, even though we had mentioned about the direction of the current. So not everything which has direction is a vector quantity. This is one of the most brilliant examples of that. Because a lot of people think something which has signs, something which has directions is always vectors. But no, it should also obey the rules of vectors. Only then it gets that title of a vector. Otherwise, it fails. It's like a driving license test or a citizenship test for being qualified as a vector quantity. Okay, but current density obeys all the rules, and that is why it is a vector quantity. But sir, how do I show that vector and how do I visualize it? Well, don't worry. So first of all, let me make you visualize current density in a very simple way. Imagine here very little current is flowing. Here a lot of current is flowing through it. Okay, a lot of current is flowing through it. In that same area, but obviously there is more current over here, versus less current over here. That is why I can say, if there is a current density vector J1 vector, and here current density vector, let's say J2 vector, the magnitude of J2 will be more than J1 because more current is flowing through that same area. That makes it more dense in terms of current. But is it necessary my cross section is always perpendicular to that flow of the current? Is it always necessary? The answer is no. Say for example, I happen to choose something like this. Look at this. Okay, want to visualize it. Okay, just imagine this conductor. I know I have sliced it at a weird angle. That's the only difference. Now, I hope you realize that whatever current flows here, whatever current will flow over here, exactly same current must flow on this side. Exactly same current should flow on this cross section. So if this cross section is labeled 1, this cross section is labeled 2, then can I say current 1 is equal to current 2? The flow is same. The flow of charges per unit time is going to be the same. Whatever charge enters has to exit. It has no place to hide, nor can one extra charge come in place. So that is why entering is equal to exiting. So current per unit, which is flow of charge per unit time, is the same. Great. But area, obviously it is different. This has less area. This is more area. You can visualize it. Areas are different. Now the manner in which we define current density properly is actually like this. Take current as it is on one side, put a dot over here, put J as a vector, and then put area as a vector quantity. So this is the right way of actually remembering what is current density in vector form. Remember, division of vectors as such is not defined, so we cannot define it in terms of division. So my dear warriors, current is current density vector dot producted with the area vector. This is the true definition in which you can represent current density as a vector form. So my dear warriors, if you use that definition over here, notice I1 and I2 are same. Areas are definitely not same. Areas are definitely not same. So I will be J1 dot A1, J1 dot A1 in the first place. I2 will be J2 dot A2 in the second place. Now let's mark the directions properly. Current density always is in the direction of the current, so J1 will be here. Current density is always in the direction of the current, so J2 will be also over here. So let me say this is J1, let me say this is J2. So this is J1, this is nothing but J2. Perfect. What about area vectors? Here the area vector will be obviously perpendicular to that surface. Here the area vector will be also again perpendicular to the surface. Remember, we have defined area vectors in Gauss's law. You take a surface, drop a perpendicular, that perpendicular is the vector of that area. So yes, area can be also treated like a vector quantity. So if this is, I will say A1, this is going to be obviously A2. Perfect. This much is done, everyone. And I hope you understand I1 and I2 both were anyways going to be equal by conservation of charge. Now comes the funny part. Notice there is no angle between J and A. There is no real angle between these two vectors A1 and J1. So angle is actually 0. So can I just not put J1, A1 and cos of 0 degrees over here and is equal to, on the right hand side, I believe there is an angle. So J2 and then you have A2. Observe carefully. There is some angle theta between these two vectors. There is some angle theta between these two vectors. So let's say I call it theta over here. Now you might be wondering, sir, what do I do with this cos theta now? What do I do with this cos theta now? Because dot product means A, B cos theta. Don't worry about it. I'll tell you why. See, if you observe this diagram carefully, you will realize one very interesting fact. This was A1, this was A2, isn't it? This was your A2. If I draw a perpendicular over here, whatever is this area will also be this area. Notice the vector of area 2 was here. So if I draw a horizontal, this was your exact angle theta. This was your exact angle theta, isn't it? So if this particular angle is theta, you can easily prove even this angle is theta. Even this angle is theta. How can you prove it? Well, one way is simple logic, guys. Hold your right hand or left hand fingers such that the thumb and the pointing finger is in perpendicular direction, something like this. Okay, something like this. Now, if I rotate my pointing finger, even my thumb will rotate. So if I rotate my pointing finger, even my thumb will rotate. If I rotate this with theta, even this will rotate with theta. Is that right? So with that logic, imagine my pointing finger was horizontal, my thumb was vertical. If I rotate my pointing finger by angle theta, even my thumb should rotate by theta. So by that logic, very quickly you will get this is theta. Otherwise, you will waste a minute or two figuring out how do I prove it, 90 minus theta, complementary angle, geometry, blah, blah, blah. Not needed. Just hold two fingers 90 degrees. This works many times and I use this technique for figuring out angles very easily. So just hold these two fingers at right angles and you see that if I rotate the pointing finger by theta, even my thumb has rotated by theta and it is perfectly aligning over here. So yes, this is also going to be theta. So when that happens, you will realize this is hypotenuse, this is perpendicular side or height over here. So immediately you will realize that cos of theta, cos theta is adjacent side by your hypotenuse, A1 by A2. That's it. If cos theta is A1 by A2, your job is done, guys. Cos theta is A1 divided by A2. Cos theta is adjacent side by hypotenuse. Your job is done because A2 and A2 will cancel. A1 and A1 will also cancel. Notice from left and right hand side. So all that I'm left with is J1 is equal to J2. Yes, that means both the cross sections have the same density of current. It kind of makes sense. Don't get fooled by thinking, sir, this area is huge. But this area is not perpendicular to the flow of the current. It is at an angle. So what is the use of having an angled surface? Because whenever I have a surface, the current should flow through it. Imagine I had a surface like this and the current is going from top and below, and in that case the current density would be perfectly zero, isn't it? This is a very interesting case. If your area is like this and the currents are going from above and below, you will see there is no density of current. There is area, there is current, but how is it piercing it? It is not piercing it. So out of this sloped angled area, it is only this component, or I would say this part of that area, which is the vertical part, which contributes in the flow of current or even in the current density. So this angled area that you saw, so this angled area that you saw, so this particular angled area that you saw can be split into, I would say, two components. One is vertical, one is horizontal. One is vertical and the other one is, one is vertical and the other one is like this. This one, the red one, there is no current density. J is equal to 0. But it is only this part which allows that current to pierce through it. So current density is definitely there. Is that clear? So that is how you can visualize this. Everyone understood this concept of how to treat current density as a vector? Area was anyways a vector. We have defined this in Gauss's law. Nothing new about it. But this kind of working is very important for JEE Advanced, because students don't know how to treat current density as a vector. They just by heart, okay, it's a vector and it is I is equal to JA dot A or JA cos theta, but you should know how this really works. And this is a very beautiful example to make you understand current density vector quantity. Alright, shall we move ahead, my dear warriors? Understood? Give me a heart, give me a thumbs up, give me okay, yes, anything, whatever. Yeah. I started close to 6:30, man. Perfect. More than NCERT line by line, we have migrated now to complete JEE Main, because see what will happen. We already have a 11th-12th channel for all the students which teaches in pure English for NCERT level. But since this is a JEE channel, so you know, I have to make sure that we do not just go to the boards part. So we made sure that we have a separate set of faculties or teachers who are taking care of the boards part, and now we are not focused completely on boards, we are focused completely on JEE Mains and JEE Advanced. That's the whole purpose. Cool? Alright. Awesome, awesome. Now that we have understood what is current density and all of it, let's go to the next terminologies. Let's try to figure out how much is basically the drift velocity. Let's figure out how much is the drift velocity. So again, we are going to take a conductor. Let's say this is a conductor, and imagine there are some electrons within that conductor and they are drifting, they are migrating just like we expect because of some field, some potential difference, whatever is there. So they are migrating like this, okay, and they have a drift velocity. Let's say the length of the conductor, let's say the length of the conductor is L. Let's say the area of the cross section is A, and let's say the current obviously in the opposite direction is basically I. Let's say the current is basically I. Let's assume that. So then what will happen is, if you wait for some time, all these electrons are just going to come out, isn't it? So this last person over here will eventually come out of this conductor, and if I have to show these people again, it's a painful process, but just visualize. After time t, all the electron, which are the charges, have crossed the conductor, crossed basically the conductor. They have basically crossed that particular conductor. How many electrons were there? How many charges were there? Well, that's something which we can calculate, or maybe it is given to me. And that number, I will call it as N, which is number of charge bearers or charge carriers, number of charge carriers per unit volume, This is very, very important. Usually it is given to you, or you can also end up calculating it. It's not a big deal. Okay, how many charge carriers are there? How many charge carriers are there per unit volume? Now there is a formula for it. It's better you remember it, because sometimes what happens, they give you the density or molecular weight and all those stuff. So it's better you remember the formula. And what is that formula? If anybody remembers, Avogadro number is there, density is also there, and molecular mass, molar weight is also there. Yes, so it is nothing but your Avogadro's number, which is Na, multiplied by density of that conductor upon the molar mass of that molecular weight of that particular element of that conductor. So let me write it all down. Na is Avogadro number, which is 6 into 10 to the power 23 approximately. Rho is density of the conductor, Then you have M, which is the molar mass or molecular weight, I can say, or molar mass of the conducting element, Perfect. That is what it is. Sometimes you also multiply it with the number of electrons per atom also. So I'll tell you why this formula comes also in brief way. So just think about it. If you have, let's say, aluminum or copper or whatever, those elements will be arranged in a particular manner. They will be either dense, sparse, however. Each element will contribute maybe 1 or maybe 2 or maybe even 3 free electrons which are available for conduction of electricity. Now, if there is some metal which contributes only 1 electron versus some other element which contributes 3 electrons per single atom, then obviously that other element is a better contributor, so there will be more charges available within that conductor. There will be more charges available within that conductor for conduction of electricity. So that is why you multiply it with N, which is basically how much is the contribution per single atom of that metal or that conductor. Number of electrons per atom. That is what you multiplied. And the rest of the things is the density, Avogadro's number, molecular mass, all of these things come because how well they are packed within that conductor decide how many such charges, how many such electrons will be there per unit volume of that conductor. Okay. So what is N? If you take a unit volume, in that unit volume, how many charges are there? If you take a unit volume, how many such charges are there? That is basically your N. Is that clear? And that number is usually very, very large. So you can notice Avogadro's number has also come, density also matters, molecular mass also matters, all of these things matter, and that's how n gets decided. Is that clear? So it is Na rho by m, Na rho by m. Everyone fine? Na rho divided by m. Got it? Everyone? Perfect. Now based on this n, current, drift speed and all of these things, we can find out how much is the drift speed. Not a big deal. So how do I find that drift speed? We think about how is current defined. Current is charge by time. So current, so let me go to the next slide now, or else it will get too cramped. Over here we had already defined what n is. So current is basically charge which flows per unit time. Now if you count the total charge which has flown in that time, if you count the total charge which has flown in that particular time, what will I do? Charge will be number of electrons multiplied by charge of each electron, charge of an electron, the whole thing divided by time. How much time does it take? How much time does this entire charge take to pass through this conductor? After time t, all these electrons have gone on the other side. So can I not say this time taken, this time which has been taken, this time which you see over here, this time is the distance that they have traveled divided by the speed with which they are traveling. Distance that they have traveled, look at this. This electron has reached here, completely crossed. It is nothing but L. With what speed are they traveling? They are traveling with a speed of Vd. So can I say this is nothing but L divided by the drift speed? L divided by the drift speed? Yes, perfectly. Therefore, current will be number of electrons into charge of each electron. Number of electrons, how do I get it? Wait a minute. If I had to find number of electrons in this, number of electrons in this conductor, in this particular conductor, here is how I would do it. Number of electrons in this conductor divided by the entire volume will actually be n, will actually be this n. Charge carriers, how many charge carriers are there upon that volume. Oh, so perfect. So from this, number of electrons will be n multiplied by the volume. And how much is the volume, guys? It is nothing but area multiplied by length. It is nothing but area multiplied by area of cross section multiplied by the length. So number of electrons in that volume, entire conductor, is NaL. Perfect. So let me just put it over here. It is NaL as it is. The charge of every electron is E, and this entire thing L divided by Vd. LL gets cancelled, therefore current is equal to N. Vd comes on the top and E is there as it is, and area is also there. Current is NVIDIA. This is a very famous formula for you to calculate the drift speed. Usually current will be known. Charge of an electron is 1.6 10 to the power minus 19. Area of cross section will be usually given to you. N will be either given or they might give you how much is the density, everything and all of that. And from that you can calculate N and then find out drift speed. So that is how it usually works. Let me show you an example so that you guys get a hang of it. Okay? Let me show you an example. Alright, shall we do an example, guys? Alright, so let's say example for copper wire, and let's take some area of cross section. We'll just take some random, area of cross section for a copper wire of I don't know, 1 centimeter square section. All right. A current of 1.6 ampere flows. Find drift speed. Find drift speed. Find the drift speed. That's the question. Let's assume density of copper is given to us. Okay, let's assume some density of basically copper. I think it is close to some iron, it is around 8,000. Copper, it is close to 9,000. Water is 1,000 kg per meter cube. 1 second. Let's say it is 9,000 kg per meter cube. Another thing, molar mass of copper, it is 63 grams per mole, and it is also mentioned each atom contributes, each atom gives one free electron. All of this is given to me. All of this is given to me, and now we have to figure out how much is the drift speed. So these are all practical data which is, let's say, given to me. All right, shall we do it now? Okay, perfect. Let's start. The first step in doing this problem is to get the value of small n, which is how much charge bearers, carriers are there per unit volume of copper. And the formula for that is Na rho by m into number of electrons per atom. So small n is Na rho divided by m into number of electrons which are there per atom contributed. Avogadro's number is 6 into 10 to the power 23. Density is given to be 9,000. Number of electrons which are contributed per copper atom, it is exactly 1, mentioned over here. The whole thing divided by molecular mass of copper, 63 gram, don't use gram, use kgs. So 63 into 10 to the power minus 3. That makes sense. 63 into 10 to the power minus 3, because that has to be in kg per mole. That's it. So solving this, I will get the value of n. I'm going to use a calculator to keep things simple because we are focusing on the concept. So let me just multiply 6 multiplied by 10 to the power 23 multiplied by 9,000, all right, divided by 63 multiplied by 10 to the power minus 3. And that answer comes out to be a very, very huge number, my dear warriors. Yeah, it is coming out to be 8.57 into 10 to the power 28. Just check this out. Just check this out. It is coming out to be very, very huge. N was not given. We had to figure it out. So it becomes a lengthy problem. If you are thinking this kind of question will not come, it has come. In fact, it has come in JEE Advanced, JEE Mains also. Okay, so you can check out the previous year papers. Okay, once we get N, now is the time to figure out drift speed. Current is NVIDIA. NVIDIA, everybody knows it's a graphics card company. So it becomes easier to remember this formula. Current is NVIDIA graphics card company. That's it. So therefore, my drift speed will become current by NEA. Current value 1.6 perfecto divided by N, which is just found out 8.57 into 10 to the power 28 huge, multiplied by E, which is 1.6 into 10 to the power minus 19, and lastly area 1 centimeter square. A centimeter square is 10 to the power minus 4 meter square. This is 10 raised to minus 4 in meter square. That's the conversion factor. A centimeter is minus 2 power. A centimeter square will be negative 4 power of 10. Now that's it. It's just a matter of calculation now. And let's see how much do we really get. So this is there. And then first I'll calculate the denominator into 1.6 into 10 to the power minus 19 multiplied by 10 to the power minus 4. Okay, it's in the denominator, so flip it, multiplied by 1.6. okay, it comes out to be very, very huge, sorry, small, my bad. So it comes out as 1.16 into 10 to the power minus 6 meters. This is in microns, guys, now. So therefore my drift speed comes out to be 1.16 16 micrometer per second, of course. Yeah. So you can see it's very, very small. Very, very small. Understood, guys? Yeah. So this is how the calculation is done, and this proves whatever I was telling you before, that listen, the drift speeds are not very large. They go in millimeters to micrometers range only. So it feels the electrons are moving slow, but it is the information of field which travels very quick and sets up electricity within the circuit. Great. This is done. Now, this particular formula is usually remembered in a slightly different way, not this way. And let me show you that. So we started off with current is equal to graphics card company NVIDIA. Take that area below. So it will become current by area is equal to NVDE. Now what is current by area? That is current density, my dear warriors. So J is equal to NVD into E. Now this equation, if you slightly modify and write it into vector form, meaning this is my current density vector. Where is current density vector, guys? Look at it. This J vector always is in the direction of the current. So my J vector should be exactly in this direction. Drift speed is exactly opposite. Drift speed is exactly opposite. Drift speed is exactly opposite. So if I put equal to, sometimes you might feel that we should put minus sign, and this is nothing but drift speed, and then there is E. But E, if I think of it as the charge of the electron, the charge itself will include the negative sign. So I don't really have to put that minus over here. I know if you put only mod, then it will be positive. But if you think of this E as the charge of electron, then the charge of an electron itself is minus E, is what you can think. Is nothing but minus E. So this is another way of looking at current density in terms of drift speed. NVDQ, okay, number of charge bearers per unit volume into drift speed into the charge of a electron. That's it. This is in vector form. And notice, very important, the charge of the electron itself has the negative sign. So minus sign will come, and it will prove that density and drift speed are actually opposite, which is seen over here. So if two vectors are opposite, they are negative vectors, guys, or opposite vectors, sorry. So there is a minus sign which should come between the equality part of those two vectors, which makes sense. This is sometimes used, very rare, but sometimes. Okay, this class duration is going to be very long, man. Yeah, maybe 5 hours or 6 hours, God knows. Yeah, it's going to take a long time. Now, once this is done, let's understand the next concept, and that is basically current density is done, current drift speed is done, current is also done. Now let's try and figure out how much is the electric field within, how much is that electric field within that conductor. So for that, we start off with something called as Ohm's law. Ohm's law. So Ohm said that if you have any device and you pass some current through it, and let's say you measure the current and measure the voltage across that device, this is your device, and you plot a table and then a graph and all of it. So you will notice that whatever current is flowing versus whatever voltage is there across that device, they happen to be proportional. So he said that if you have something called as a ohmic device, then the voltage difference is directly proportional to the current, and this constant of proportionality is what we call as resistance. How much resistance is there to the flow? R. This is the constant of proportionality. So this is basically your Ohm's law, which defines how do we find resistance. So think about it. If the resistance is large, then for a particular voltage to keep a large value of resistance, the value of current will go down because their product should remain as the voltage, which is fixed. If the resistance of the device is very low, then it allows the passage of a large value of the current. So resistance decides how much current will flow if the voltage is fixed. That's how resistance has been defined. This unit of resistance, as you can notice, voltage and current. So a ohm of resistor is nothing but for an ampere of current, there should be 1 volt of potential difference. So that is the unit of resistance. Sometimes you use this symbol. You might have studied all of this. So 1 ohm is when there is 1 volt difference for 1 ampere of current. So that resistance is called as 1 ohm. Now this resistance depends on multiple things, like what is the material, what is the shape, size, that means the geometry. It also depends on what is the temperature, all of these things together. It depends on all of these things together. That's how a resistance, 5 ohms, 100 ohms, 1 kilo ohm, 15 mega ohms, it depends on what is the size of the conductor, which material is it made of, aluminum, carbon, some material compound, and what is the temperature at that moment. Now if you see the graph of voltage versus current, this is how it will look. This is how it will look. This is your voltage, this is your current. So this graph for voltage proportional to current will look something like this. No voltage, no current. This is voltage proportional to current, and this is only true for a ohmic device. Now most of the metals, regular metals, are ohmic devices. At that point of time, Ohm gave the law. Later on, people realized there are so many things like vacuum diodes, semiconductors, some compounds, and so many other materials which do not obey Ohm's law. And then you notice that these kind of materials have some different kinds of graphs. Some materials give a graph like this. Some materials, they have a graph like this. So, their voltages are not proportional to the currents. They are called non-ohmic devices. Non-ohmic devices. Now, what people think is that Ohm's law means voltage proportional to current. Yes, that was the whole purpose of it. But then we later on modified this and understood Ohm's law in a slightly different way. Ohm's law is not necessarily voltage proportional to current. Rather, it gives me the definition of resistance. How? Observe. Imagine, I tell you, there is some random graph of voltage and current, and I tell you, this particular non-ohmic device follows this random weird curve, something like this, and I give you certain values. Okay, let's say this happens to be maybe 2 amperes, let's say this happens to be 4 amperes, let's say this is 1 volt, or let's say this is 10 volts, let's say this is I don't know, maybe 60 volts or maybe 80 volts, or no, some random volts. Okay, I've just taken it like that. This is 100% a non-ohmic device. So if you consider the very first point at point 1, if you use V is equal to IR, voltage is 10, current is 2, resistance is R1. So R1 which will be 10 divided by 2 will become 5 ohms. Is that right? Resistance at this point becomes 5 ohms. Resistance is voltage divided by the current. Now if you find the same thing at point 2, notice what will happen at point 2. The voltage is 80 volts, current is 4, resistance is R2. So R2 will be 80 divided by 4, which is 20 ohms. Clearly the resistance is changing. But what I got in return is how to find resistance at any voltage or current. So rather of looking at Ohm's law as V is equal to IR, because mathematically this is not wrong, I would suggest physics wise think of Ohm's law as the definition of current and resistance is voltage by current. This is the right way of looking at Ohm's law. It tells me how to find resistance for any voltage or any current. Lot of people I've seen what they do when these graphs are given. Surprisingly, they draw a tangent to the curve and then they try to figure out dV by di and then they write that as resistance. No, that is not resistance, guys. Okay, resistance is simply that voltage and that current divided with each other. No slope, no tangent, nothing. Okay, so please don't draw tangents and slopes for such curves. Okay, a common mistake, a very, very common mistake. Absolutely clear? Very good, very good, very good. But you know what? There are problems where you might have to draw tangents. Yes, there are questions where you might have to draw tangents. We'll come to that. But remember Ohm's law, where voltage proportional to current, that is true till an extent for only ohmic devices, but voltage is not necessarily proportional to current. It could be non-linear. So non-ohmic devices are there, which are compounds or semiconductors, vacuum diodes, so many things are there. So that's why we modified it and said, okay, no problem, I defined resistance from Ohm's law for a particular voltage and current. Cool. So sir, what kind of problems you might have to find the slope or the tangent you have to draw and all of it. So those kind of problems happen to be like this. You define another term called as dynamic resistance. Dynamic resistance. And this dynamic resistance, guys, instead of just V by I, is actually dV by di. This is completely different. This is how the voltage changes for a small change in current. That's a completely different story altogether. Okay. Here, obviously, we talk about derivatives and tangents. So, if I have this as voltage, this is my current, and then you have some random graph. So, if you want to find dynamic resistance, okay, first I will draw the tangent. It will be easy for me. Now I will draw my graph. See, now it will be easy, isn't it? Okay, so at this particular point, I want to find what is the resistance. So draw the tangent, and that is what will give me my dynamic resistance. This is the tangent, this is theta. So this is the slope of the tangent to voltage versus current graph, which is the same as tan of theta. Okay, so in this particular example, if dynamic resistance was asked at point 1, I would have drawn a tangent. I would have measured the angle. I don't know, it could be anything, guys. Let's say this angle came out to be 37 degrees. Chumma, I have put some random angle. I don't know really whether it is 37 or not. So if I had to find dynamic resistance at the point 1, R dynamic at 1, then it will be dV by di, and that is nothing but tan of 37. I have drawn the tangent and marked the angle. Tan 37 is 3 by 4, which is nothing but 0.75 ohms, which is way different from 5 ohms. Okay, got it? I'm so glad, Rocky, you are understanding it. Sir, R is equal to VI will only work for, yes, R is equal to, see, understand the difference between V is equal to IR and R is equal to V by I. Mathematics wise, it is the same, because if you ask a maths teacher, they're like, oh, nothing, same thing, man. Current, you have taken it below voltage. Correct. Perfect. But the way I interpret it is slightly different. When I'm writing it over here like this, I feel that, you know, voltage was proportional to current and R is doing the role or playing the role of a proportionality constant. But when I write R is equal to V by I, it feels like I'm more authoritative in deciding and asserting that, listen bro, R is defined as voltage by current. So this makes it the definition of resistance saying, no matter what device you give me, ohmic, non-ohmic, etc., R can be found if you tell me voltage at that instant and current at that instant. I am not saying voltage will be proportional to the current. I am not even saying that resistance will be constant. I am just saying I can give you the value of resistance. So V is equal to IR does not really mean, or R is equal to V by I does not really mean voltage is proportional to the current. It happened so earlier. This formula came from ohmic devices but was later on applied to other devices also, because you could define resistance. That's all. So it started, the story began with proportionality, but it ended up being applied to non-proportional devices, which are non-ohmic devices. Is that now clear? Music, thank you so much. Welcome aboard. Perfect. It's Zabi, Kwajam, Rocky. Everybody clear? Rasik Kuju. Understanding this concept. I bet many of you did not know this. Many of you did not even realize that Ohm's law was actually so much more than what is written in NCERT or probably even explained otherwise by many people. Yeah? Great, great, great. Now that we understood resistance and we just spoke about resistance depends on the temperature and blah, blah, blah. So let's go to that aspect now. We are focusing on this aspect, the dependence of temperature, dependence of resistance, my bad, on these parameters. Okay, let's start with temperature. It is very easy actually. So for conductors, resistance increases with temperature. And the reason for that is when temperature increases, average kinetic energy and speeds increases. So the number of collisions which happen between electron, atom, all these things, they increase. More collisions means it's more difficult for the electrons to pass through the conductor. Think of it as if you are on a path or a footpath or a road or I don't know, a platform or a stairs, and very few people are there and you are not bumping into many people. It's very easy for you to cross that road or path. But imagine the road is so crowded, or forget crowding. Just imagine people are moving very fast. They are in a hurry. You are bumping into everyone. Everybody is trying to figure out their way. You hit someone. You have gained momentum. You hit. Because you hit, you have to change direction. Again, you go somewhere, hit. And again, then you come back. Yes, your speeds are good. But you are bumping very frequently. That creates a problem. That creates more resistance. And that's why resistance increases. The flow of current reduces. The flow reduces, and that's why I can say resistance increases. Is that clear? That is the logic behind it. Now, what happens is, if you draw the graph Now if you draw the graph for resistance versus temperature T, this is not time, this is temperature for conductors, you will notice that this graph can go maybe like this. Okay, it need not be a straight line, it could be a curved line, some non-linear curve, but that curve is not so curved that you can feel it very nicely. It's a slow curve. It's a curve for sure, but it's a slow curve. But if you take a small range, notice, if you take, for example, a small range, if you focus your attention on a small range of temperature, oops, what is this? How do I go back? If you take a small range of temperature, you will quickly realize that in that particular small range, the temperature is barely seen to move like a curve. It feels almost like a straight line. That means linear variation. Now, how much is usually that small range? Not 0.1, 0.5 degrees Celsius. Usually it happens to be couple of tens to hundreds of degrees Celsius or Kelvin, right? Because I said it is a slow curve. It does not change, the curviness does not change very quickly. So even for some 50-60 degrees Celsius, usually it's seen to be a straight line. So for a good deal of range of temperatures, you can assume linear variation because it feels almost like a straight line. And that is the reason why we will say the resistance dependency for a decent range of temperature is given by resistance at particular temperature T will be resistance initially 1 plus alpha into delta T. This is very similar to linear expansion formula from the chapter of thermal physics. So, my dear warriors, these terms are exactly just like before only, where you have studied in linear expansion. Original length into 1 plus alpha delta T is the final length of that rod. You have studied this. So, alpha is over here called coefficient of thermal resistance. Coefficient of thermal resistance, usually it will be given to you, or if it is asked, that means other things are given to you. This is delta. Delta means change. T means temperature. So, change of the temperature. Change of your temperature. These are your usual terms. Initial, this is final. Alright. So, resistance at, let's say, 0 degrees Celsius. This is a resistance at some other degree Celsius. So, something like that. So, this is your, new resistance after temperature change. So, say for example, it is given to me for a metal, alpha is 2 into 10 to the power minus 3 per degree Celsius, and it has a resistance of 50 ohms at 27 degrees Celsius. Find the resistance at let's say, I don't know, maybe I can just say 77 degrees Celsius. Chumma randomly I have taken 77 degrees Celsius. What is the new resistance at 77 degrees Celsius? So I know the original resistance at what temperature. I want to find what is the resistance at some new temperature. Alpha is also given to me. So if you look at this formula, most of the terms are known, only the unknown is the new resistance. So let's use that. So therefore, my R, which is R naught, 1 plus alpha delta T. In this question or formula, R naught will be original, which is 50 ohms. 1 is as it is, alpha is already given, thermal resistance coefficient. Alright. Change in temperature. If you notice, delta T is 77 minus 27, guys, which is 50 degrees Celsius. So that is the change of temperature. So I'll just put 50 over here. So this will become 50 into 1 plus 2 into 50 is nothing but 100 into 10 to the power negative 3. So this will become 50 into 1 plus, this will become just 0.1. So this will become 50 multiplied by, or this is, 50 into 1.1. So 11 into 5 basically, which is nothing but 55 ohms. So that 50 ohms has now become 55 ohms. That's all. Yeah. NID के लिए yes 75% चाहिए. तस्मिन all these government top-notch colleges 75% is mandatory. IIT, NITs, that's the common rule. Okay. Now that we understood, yes, temperature does depend on, resistance does depend on the temperature, and for small ranges, you can say linear variation is there. Now, what is the other things that it depends on? So, temperature aspect taken care of, material and geometry. So, let's focus on that. So, let us focus on that. One second. The next aspect on which the resistance depends on is the geometry. So for that, if you tell me this is the conductor, having some area, having some length, and I want to know what resistance does it have, and the symbol for resistance in electrical circuits is this. Like for batteries it is this, for switch it is this. So these are the electrical circuit symbols. So I want to know what is the electrical resistance for an area and length. Experimentally it was found that the resistance is directly proportional to the length and inversely proportional to area of cross section. So then the constant of proportionality is called rho. And this is not density, guys, don't get confused. So rho L by A is the formula for resistance. Like you can see, it depends on the shape, geometry, size basically, how much length it has, how much area it has. That tells me the resistance. Now this rho is called as resistivity, resistivity of that material. This resistivity is different for different materials. Accordingly, the resistance will change. Now, this unit of resistivity, you can guess what it will be. Resistance is in ohm, length is in meter, area is in meter square. One of the meter will cancel. When this meter multiplies with ohm, so the unit of resistivity will be ohm meter. Ohm meters will be the SI unit of resistivity. So, resistivity is completely dependent on the material, depends on the material. So now we have taken care of literally everything. As you can see, resistance depends on material, geometrical shape, size and the temperature. Temperature aspect I already told you, R naught 1 plus alpha delta T, that's the formula. R is rho L by A, takes care of the above two. Material decides resistivity, length and area is basically the geometry. So, in all, we have seen how resistance can change with any of these three things. Be it temperature, be it the material, be it the length or the area, which is basically the geometry. Sometimes you might get a reciprocal of resistivity which is called conductivity. So you might use the symbol sigma, which is 1 by rho. This is called as conductivity. SI unit will be exactly opposite of it. So it will be ohm inverse meter inverse. Ohm inverse meter inverse is the SI unit. So conductivity is opposite of resistivity. If a material is more resistive, does not allow more current, it is less conductive. If a material is less resistive, it is more conductive. So that's why reciprocals, as easy as that. Great. So imagine there is a question which is given to me and I see one table and I find that there is a metal whose resistivity is, let's say, 4 into 10 to the power minus 6 ohm meter. And I see that there is a cuboid of dimensions 2 meter multiplied by 4 meter multiplied by 6 meters. Okay, let's visualize this cuboid. It's going to be interesting. 2 by 4, okay, 2 and let's say this is 4, okay, and by 6 meters. Interesting, all right, okay. Now I want to find the resistance. I want to find the resistance in 3 different scenarios and I'll tell you what are those scenarios. First scenario, I pass the current from here and take out the current from here. Second scenario, I pass the current from the top and take out the current from below. Third scenario, I pass the current from front or right side and take it out from the left side. 3 different scenarios. 3 different resistances. How we are going to use these formulas? When the current passes like this, remember this will be actually the area of cross section which you will be considering, across which the current is passing through. This is that other area of cross section, guys, over here. See if you are able to visualize this. Yeah, this is the area of cross section through which the current is passing by. So if I had to find the resistance, which is rho L by A, rho is 4 into 10 to the power minus 6, no doubt. Length is 6 meters. This is 2 meters. This was 4 meters. Length will be actually 6. Area of cross section will be 2 into 4. So it will be 6 divided by 2 into 4. Got it, guys? 4 will cancel. 6 by 2 is 3. So it will be 3 into 10 to the power minus 6 ohms, which is extremely small, which is what might be expected from a conductor, that it will have very less resistance. Isn't it? Understood? Sir, why are you taking class? I have now come under existential crisis, man, because of your question. Now, next question will be, sir, why are you breathing? Next question will be, sir, what are you doing with your life? Don't put me under depression, man. Such questions you are asking me. My God, I should also ask you then, what are you doing over here? What are you doing with your life? Right? What are we humans doing over here? Why is the universe existing? So all sorts of questions, are there with me also. We can sit and probably discuss all of this. Next, if it is like this, then there is a small difference, guys. What will happen? This will be the area of cross section, right? This will be that area of cross section through which the current is passing. And in that case, my resistance, which is rho, which is 4 into 10 to the power minus 6, length will now be this height, which is 4. This was 2, this was 6. So now length will be 4 and area of cross section will be basically 2 into 6. So you can write 4 cancels, 2 cancels, this will become 3, 4 by 3. So it will become 4 by 3 into 10 to the power negative 6 ohms. And in the third scenario, when it is going like this, you can easily notice this is that area of cross section through which it is piercing, and there is one more over there, but unfortunately I can't show it so well. I will try something like this. Yeah. So in that scenario, my dear warriors, this is 2, this is 4, this is 6. How much will be the resistance? Rho is 4 into 10 to the power minus 6. L, length is only 2 meters. Area is 6 multiplied by 4. 6 multiplied by 4. 4, 4 cancels, 2 by 6 is 1 by 3 into 10 to the power minus 6 ohms. Got it? So this is how you can visualize how to use rho L by A formula. Sir, in PYQ question, is that graph between resistivity of and temperature for conductors which is straight line for a wide intercept but does not mention for short period? So usually we understand it for short period only or small range unless specified otherwise. So even if they don't mention small range, we will almost take it linear only, because most of the conductors for a decent range, hundreds of Celsius, it's straight line. So only for an extreme range it becomes non-linear. Okay. Clear, guys? Everyone? हाँ, awesome, awesome, awesome. सर का नाम क्या है? सर का नाम है कैप्टन श्रेयस. समझे कि नहीं? Okay. Now, next question. This is one of the most commonly asked question, guys, and that is basically a wire is stretched. A wire is stretched to 3 times, 2 times, 4 times, then resistance becomes how many times? That is the question. Resistance will become how many times? Very commonly asked question, guys. So for that, the logic is, imagine originally this was your wire. You have elongated it like this. When you elongate it, what happens is, yes, the length will increase, but even the area will decrease. So the wire will actually become thinner. And many people ignore this concept that area will also change. So in this process of elongation, it is the volume which remains constant. Volume which remains constant. So if old area was A, old length was, let's say, L, then the new area is, let's say, A1, new length is, let's say, L1. So this is how it works. AL is equal to A1 L1, volume is basically constant. Now if you focus on the resistance, which is R is rho L by A, so the new resistance will be rho L1 by A1. Notice what will happen to A1. A1 is AL by L1. It is AL by L1. Can you see that? What is area 1? Area into L divided by L1. That is what I have substituted it over here. L1 goes on the top. So it will become rho by AL multiplied by L1 square. Notice rho by AL, something did we miss? Rho L by A, yes. Area is equal to AL. I substituted even as yes, L1 square happened. One second, guys. A1, L1 square, rho by AL. Why did we get rho by L over here? Did I mistake into something else? This is the rho L by A. This is the new length. This is the new area. Yep. So over here, if I see what is the new area, it will be area into length divided by this particular L1. Perfect. So if I substitute A1 over here, what will I get? Notice this will be rho into L1 divided by, instead of A1, I will write it as area multiplied by L, and that L1 square will come. Oh, the moment I see L1 square, you should realize that what is happening over here is there is a square dependency of a resistance. So if you have to rearrange it, I will write it like this: rho by A L square, and rho L by A like this, and then L1 by L whole square. I did it deliberately because anyways L and L cancels off and you will still get back this original expression. Now you can see this is nothing but my old resistance into L1 by L is number of times that you have stretched it whole square, because L1 by L is new length by old length. So if it is 3, 4, 5, 6, accordingly this ratio will change to the number of times that you are stretching it. So the new resistance is the old resistance multiplied by the square of the times that you are stretching it. So in this scenario, as you can see, it is 3 times. So the new resistance will be old resistance multiplied by 3 square, which is nothing but 9R. Hence, the answer will be 9. If it is 2, it will become 4. If it is 4, it will become 16. If it is 5, it will become 25 times. That is the explanation or logic for this. Is that clear, everyone? Yeah. So stretching of a wire not only increases the length but also reduces the area. So it has a double effect over here. Great. Now that we have understood, okay, how resistance depends on length, area, everything. Now there is a very interesting thing which I am going to show you. Observe carefully. Observe carefully. R is rho L divided by A. Is that right? R is rho L divided by A. Also, definition of resistance is R is voltage divided by current. Yes, sir. How about equating both the sides? So we write voltage divided by current over here, and then on the left hand side rho L by A. Therefore, rho L by A and voltage by current. Now let's play around with this. Let's play around with this and see what do we really get. Okay. So first thing first, okay, I will write down voltage over here. This length I will bring it down over here. This current I will bring it on the top. Let me keep area over here. Resistivity is as it is. Resistivity is as it is. Okay. See if you understood. Length I have brought down. Current I have brought it on the top. Everything else is as it is. Now let me start thinking what each of these terms are. Current by area. Wait a minute. I know it is density of current. Voltage per unit length. dV by dr is the electric field. Rearranging it, therefore I am getting the electric field is rho J. Rho J, that is what I am getting, or J rho. E is equal to J rho. E is equal to J rho. Now compare this with Ohm's law equation. Compare this with voltage is equal to current into resistance. This equation was valid for a big conductor. There is some voltage across it. There is some current passing through it. It has a resistance. Now you make it more specific. Voltage per unit length is electric field. Instead of just current through the entire conductor, you make it current per unit area. You will get J. Instead of taking the resistance of the entire thing, you make it per specific length, per specific area. That becomes resistivity. So this is very similar to Ohm's law. That's why I have written it over here. Just compare it, my dear warriors. This is for the entire conductor. This is for the entire conductor. This is more specific. This is more specific. That is the only difference between these two. So that's how you can find out the electric field. E is equal to J rho by just comparing it with Ohm's law, and I just showed you what's the derivation like. Isn't it right, everyone? Amazing, isn't it? Now you can get plenty of equations from this. Say E is equal to J rho, just like V is equal to IR. Instead of that, E is equal to J rho, and instead of rho, I can write this as 1 by conductivity. I can write it as 1 by conductivity. And J, wait a minute, I remember from my drift speed formulas, NVDE, yes, NVDE. Oh, okay, so E is equal to NVDE, and then there is sigma over here. Rearrange all these things if you would like, and you can get drift speed is equal to E sigma by NE, and all sorts of equations. You can rearrange and play around with it. Yeah, that is what you can see. Is that right, my dear warriors? You can play around and get a lot of things. But even before playing around with them, one more thing which I would like to tell you. There is one more formula for finding drift speed. And it looks something like this. You take an electron, it accelerates, it acquires some speed, that is drift speed. You find how much it accelerates by, which is force divided by mass. Force is the charge multiplied by the electric field. Mass of the electron is m. From this, you find how much is the drift speed using kinematic equation, u plus acceleration into time. So that acceleration being e by m, and that time given a different symbol called tau. What is this tau? This tau is called as relaxation time. This is called as relaxation time, and this relaxation time is basically the time for which literally the electron relaxes from one collision to the next collision. If you remember, in kinetic theory of gases, there was something called as mean free path, where a molecule collides with a molecule and then freely moves till the next collision, and that average distance was the average free path where that molecule relaxes, travels in a straight line. This is exactly like that. So from one collision of an electron to the next collision of an electron, it travels freely. It basically relaxes for that time. So this is a collision to the next collision. So during that collision, that average time that it takes is called as the relaxation time. And that relaxation time is related to the drift speed by this particular formula, by simple kinematics, Newton's laws, acceleration, force, everything. So if you want, you can even use this drift speed over here. You can even use drift speed formula over here and see what do you get. Where does it go? EET by M. E drift speed is EE tau by M. EE tau divided by M. That is your drift speed. Rest all are same. N is there, E is there, and of course your sigma is there, and this E is also there. This E and this E has gone, and if you want, you can shift other things. So one will be N tau E square by sigma M, N tau E square by sigma M, and if you rearrange this, you will get conductivity. Conductivity goes on the top, will be N E square tau divided by M. N E square tau divided by M. This is also a very famous way of writing and rearranging all these equations. So conductivity is dependent on how much time it relaxes. If it relaxes for a long time, that means it is traveling very freely. So the conductivity is great. So it is more conductive, less resistive. If that relaxation time is less, so it is colliding more frequently, So the conductivity is less, resistance is more. So this is another way of looking at resistance or conductance via the time for which it relaxes, which again depends on how frequently they are colliding. Yeah, so this is the derivation for that, and I've just shown it to you. So at the end of the day, it's just manipulations, like you can see. So if you understand these equations, where they come from, it becomes easier for you to manipulate. Perfecto? Clear हो? सर आप कौन सा सब्जेक्ट पढ़ाते हो? What should I say, man? Ayo, why are you asking such? What has happened to the chat box? My God, guys, really? Ayo, sir, why are you teaching? Sir, what subject are you teaching? Ayo, I don't know what has happened to the chat box today. Something has happened. Something is in the air, I feel now. Yeah. So all of these things done. Most of the current parameters are also done. So we'll take a small break. We'll take a small break and then we will return. Okay. I will also have my dinner. You also have a dinner and we'll return. Okay. Cool. See you. I hope I'm audible and visible to all of you. Yes, good evening. Back, welcome back. It's time to continue ahead. Let me just check if I'm. One sec. Yeah, everything is fine. Okay. So I joined lately. So should I revise? Yes. So please complete whatever you have missed properly. Don't just revise, because revision will just go bouncer. You will do superficial things, not in detail. So better to do it properly, because the first few chapters, especially in physics, very heavy, very intense, very conceptual. It's not like electromagnetic waves or even wave optics, or even for that matter, other topics like modern physics, which are not so conceptual, so lengthy. It's simpler, So electrostatics, potential, capacitance, current, electricity, very deep conceptual chapters. So do it properly, not just one shots. Okay. Okay, perfect. So an electron moving in a loop should produce zero current, as it resembles the case of conductor, which is not given a potential difference where the electron reaches its initial position. So it's not like that, man. I mean, don't take it literally. It is like a current carrying loop. I did not say it is a current carrying loop, because what happens inside a conductor, the electron loses its potential because of resistance, because of the wire. But if that wire was a superconductor, then it would never need a battery, and it would for indefinite period continuously go around in that loop of conductor. So think of a superconductor in which the electron is continuously circulating without ever needing any kind of potential difference. Think of it like that. Alright? Because a charge going in a circular path is not stopped, it is not colliding, it is not hampered in any way. It's free, it's just rotating. That's all. So it is a case of zero resistance there. Okay. Amazing. Let's go to the next concept. And now that we have done a lot of things over here, okay, first of all, let me just save this, guys, so that I don't lose my notes. Now we are going to the concept of electrical power, and then a very important theorem, which is power transfer theorem. And before that, actually, we should go to something called as cells, combination of cells, and then resistance, and then actually we can go to power. Okay, so let's start with the resistors, cells, combination of them, all of that. But before that, what is a cell? A cell is nothing but the powerhouse, like they say mitochondria, powerhouse cell, and all of that. Same way, a cell is a powerhouse of your electrical circuit. It powers that circuit. So this could be your circuit. It powers up that circuit. It powers up the circuit. It provides energy. It powers it up. That means it supplies energy to a circuit. And the way it does is by converting chemical energy. Now this particular chemical energy is stored in a cell, stored in that particular cell, and that converts itself into electrical form, into electrical energy. And you will notice, by the way, this is the symbol of a cell. You would have seen, you would have noticed what it does. A cell, it flows, it makes the current flow into that circuit, and when that current flows, basically a charge is taken from a lower voltage to a higher voltage. Charge flows, there is a charge which flows through the terminals, through the terminals of the cell and it goes from negative to positive. So basically there is a change of potential for a charge. So whenever a charge is taken through a potential difference, work has to be done, and that work comes from chemical energy. So there is a conversion of chemical energy into electrical energy, electrical work which is being done, which is also a source of conversion of that energy. And that electrical work is nothing but how much ever charge you take multiplied by the potential difference. How much ever charge you take multiplied by the potential difference. Multiplied by the potential difference. Very, very important. Okay. So if 5 joules of chemical energy stored in that cell gets converted into electrical work, so that 5 joules of work is being done on some coulombs of charge to cross it across some voltage difference of the battery's terminals. Keep that in mind. In fact, that is how we define something called as the EMF of that battery also. That is how we define something called as the EMF of that particular cell. It is nothing but how much work has to be done, take that charge below per unit charge to move it from lower to higher voltage. That is that potential difference across those cells or the terminal, sorry. So the EMF of the cell, which is also exactly that potential difference, is how much work needs to be done to take that charge from lower to higher, from negative to positive. So EMF of that cell is work done to move that charge from negative to positive per unit charge which flows. Per unit charge which flows. So that is why you will see the unit of EMF is joules per coulomb, which is also volt. So EMF is having an unit of joules per coulomb, which is nothing but a volt. Simple. This is that EMF. So you will see that symbol E which comes with that battery. So that is called as the EMF of that cell. How much joules of work you are doing per coulomb of charge. How much joules of work you are doing per coulomb of charge. And that work needs to be done because you are moving that charge from a lower terminal to a higher terminal in potential. Okay. Rohit, I can talk in Hindi, man. In fact, there is another channel which is the Maharashtra channel in which I am teaching in Hindi only. So you can watch that channel. But this channel is a pure English channel, and I am not talking very fancy English, Shakespeare English, Sashi Tharoor English. No, very laddu English only. Because I want many kids who learn in English medium, who think in English, and because the paper is in English, you think in English. In future also you will be using English in companies, in MNCs, you go abroad, whatever. Plus a lot of people who do not understand Hindi. That is why this channel is there. So let's not dilute this channel. Let's not ask again and again, sir, please teach in Hindi or that thing. Because the reason why this channel exists or I exist is because many kids used to ask, sir, please teach in English. Now, so many channels in Hindi, so many channels in other language, but in English we want to learn. Alright, so let's not get there. Cool. Alright. So now that you understand what an EMF is, basically, realize that whenever you have a cell, you might encounter some small resistance within that cell, which is called internal resistance. This internal resistance is encountered within the cell due to the small resistance in the electrolytes. So that cell might be made of nickel, cadmium, lead, acid, whatever is there. So when those electrons travel inside the cell, then also there will be some resistance. So that resistance is called internal resistance. If there is a very special case, the internal resistance is 0, then that is called as an ideal cell. It is a very hypothetical cell. No such cell exists. It's ideal in nature. So it only has just an EMF and nothing else. There is no resistance within that cell. But all the real batteries will have some deal of resistance within of it. Yeah, very good, clear. What happened to my chats? Okay. Now there are different ways in which you can connect a cell into the circuit, and you should understand this very, very well. First, you take a cell, a real cell. It has some EMF, some internal resistance, and connect it to some circuit. That circuit to which you connect it is always called as the load, and the symbol of that load is R, meaning it will have some of its own resistance. You are loading the battery, means you are giving it something to do, some work to do, some energy to deliver, right? So it's a load. Okay. So this battery has been loaded with some resistance R. So it will deliver that energy to that load via that resistance. So there is going to be some deal of current within that circuit. I will call that I. And by Ohm's law, I can easily figure out what is that current and all of it. Not a big deal. So you can see the resistance of this entire circuit, the net resistance is R plus R. The net voltage, the net potential difference is basically E. So using our Ohm's law, very simply, I can say that voltage is whatever is that current multiplied by that total resistance. So therefore, my current will be EMF divided by R plus R. Total resistance is R plus R. The total loading EMF is E, or voltage difference to that circuit is E. So current will be E by R plus R. Very straightforward. Now if you see over here, it is very easily seen that if my load increases, R increases, denominator increases, current will go down. If my internal resistance of that cell increases, then also my current will come down because it is in the denominator. Alright. Now in these kind of circuits, I will say that listen, the chemical energy in that battery, chemical energy in that particular battery went on to deliver some energy into the circuit. It did some electrical work. It did some electrical work in moving those charges. Such a process for that cell is then called as discharging. The cell is said to be discharging. So discharging means the chemical energy gets converted into electrical work. Clear till this point? Very good. Now when a cell is discharging, if you happen to measure what's the voltage across the cell, remember this is my cell together, right? The resistance is within that cell. If you ask me what is the voltage across that cell, please note it is not E. It is a voltage over here or here or here or here. It's one and the same thing. That voltage is whatever current is passing multiplied by the resistance. That particular voltage is the current which is passing multiplied by resistance, simple Ohm's law. This voltage which is measured across the ends of the cell, this is not the ends of the cell because remember there is an internal resistance also. So truly these are the ends. End means terminal. So this voltage at the ends is called terminal voltage. So my terminal voltage of that particular cell V is nothing but current multiplied by that resistance, but current I already know it is E divided by R plus R, and this multiplied by R. If you want to rearrange this, it will become like this: E multiplied by R plus R. This is a very interesting looking formula. Notice how voltage is lesser than E. Yes, the terminal voltage is lesser than the EMF. This is a very important finding, my dear warriors. Why? Because if there is a cell and it says that it is a 1.5 volt cell, you connect it in the circuit, you will notice the voltage in that cell is no longer 1.5, it is lesser than 1.5. E will be that 1.5, but the actual voltage that you will get across the ends of the cell will not be 1.5, it will be 1.4 or 1.3 or 1.47, like that, but anything which is less than 1.5. Why is it? This is the culprit, like you can see over here, this extra R, which is making the denominator bigger. Otherwise, this would be R by R, means V will be equal to E. So the internal resistance is the culprit, which sucks away some of the energy within itself, which makes sure that when you measure the voltage here, it is lesser than what you would measure across these two ends. This would be 1.5, but this would be always lesser than 1.5. So internal resistance is sucking away some of our energy, it is causing some loss. That's why the terminal voltage is lesser than the actual EMF of that cell. Is that clear? What is the meaning of EMF and what's the difference between EMF and the voltage that you end up measuring in the terminals? It is completely different. Okay, so this is your discharging of a cell. What was this? This was discharging of a cell where chemical got converted into electrical work. Now we are going to do the exact opposite of it. Imagine you have a cell like this. Think of this like your battery over here. EMF is E, R is the resistance, but this time you are not connecting it to a load, rather you are connecting it to some another battery. The positive is connected to positive, negative is connected to negative. Crazy, guys, this is to some another power source, you can say. This is our power, this is our external power source. So this time you will notice that the current will go inside like that and come out from here like this. Here the external power is the one which is giving energy into the battery. So I will say the external power, external electrical source of power or energy is giving that energy to that cell, and the cell is storing it, in chemical form, in the form of chemical energy. So this is exactly opposite, and this is no longer discharging, rather it is now called as charging of a cell. You might have seen rechargeable cells, they exactly work on this principle, where the positive to positive, negative to negative. So the external energy goes and gets stored inside the cell. So there is a reverse chemical reaction happening and that energy is getting stored within. So the current is entering the battery. Notice over here the current was exiting the battery, leaving the battery, right? Current was leaving the battery here. Here the current is entering inside the particular battery. You will notice that actually when you in fact work around this problem, you can also prove it. Okay, it's not that difficult. Also that V will be EMF minus I into R. You can try out. It's not that difficult to prove this. Here you will notice the exact opposite. If you measure the voltage across the terminals of the cell, if you measure the terminal voltage, the terminal voltage will no longer be E minus IR, but it will be actually E plus IR. Now this you can easily get it by a law called as Kirchhoff's voltage law, which I have not yet touched. I will be teaching in the later part of this lecture. So right now I have not elaborated much on how you get this. You can get it easily, it's not a big task, but with Kirchhoff's law it becomes very easy. But same thing over here, even with Kirchhoff's law you can get it. Notice, so I'm more interested right now in the outcome than the process. Notice over here it is E plus IR. That means the voltage across those terminals is more than the EMF. Think logically, why is this happening? Why is it that you need to have a power which has more voltage than the EMF? Meaning the cell is of 1.5 volts, but the external power will be more than 1.5, meaning like 1.6, 1.7, 1.8. Why that extra? Because this culprit is internal resistance. It will suck away some energy. You are giving 1.7 volts, but only 1.5 volts of voltage is needed to charge it. Why is that extra 0.2 needed? It's getting actually wasted in that internal resistance of that cell. Understood? That's why the voltage is more than EMF. Is this absolutely clear? Okay? Absolutely clear? Okay, fine. I will just check the resolution later on. But from my side, I usually send it in high resolution only. So I will definitely check it. Okay. You can continue with this lecture, Krishna, because the part where you needed electrostatics is mostly over. But still, I would suggest continue with this lecture as much as possible. You will go with the flow. At least this chapter will be done. You will understand a lot of things. After that, again, you can continue with electrostatics later on. Okay? Okay. Okay. Perfect. All right. Awesome. Awesome. Now, this was charging. This was discharging. The next type of connection for a cell, is not connecting it only. Yes, literally not connecting it at all. This is your EMF. This is resistance. That's it. Nothing has been connected. Such a circuit is called as open circuit, open cell or open circuit, not connected at all. So in that case, there is no loss or change or conversion of energy. The cell does not supply, nor does it get any kind of energy. It's just there. It's just open. Where will it give the current? So obviously, the current in this circuit is going to be 0. And if there is no current in the circuit, what happens is, when you measure the voltage across the terminal, that voltage always equals to be E. Say current is 0. So look at these formulas. I is 0. Whatever is R doesn't matter. V will become equal to E. Even if you take this particular section, current is 0. V will become equal to E. So when current becomes 0, doesn't matter whether it is charging, discharging, even if it is, it doesn't matter. Current, if it is 0, gone. That's it. That's it. There is no loss in that resistance. There is no energy which is required by that internal resistance. So voltage will become EMF. So the terminal voltage becomes equal to the EMF of that particular cell, becomes equal to the voltage of that cell or EMF of that cell. This is the only situation where it is equal. So whenever there is a process or an experiment or a procedure to measure EMF, you will always see that they try to measure the open circuit terminal voltage. So whenever you don't allow any current, if you use a voltmeter and measure the voltage, that will give me the exact value of that EMF. Got it? No current at all. Makes sense. The other extreme of this is you take that cell, okay, you take that particular cell, and I'm pretty sure you would have done this as a kid, and you connect but without any load. Think of it as a load of 0 ohms. This particular arrangement is called as shorting, short circuit, shorting a cell. Short means you are connecting two things together, that is called as shorting. So shorting a cell meaning taking the terminals of a cell and connecting it with each other. If there are two wires of cables of electricity and I said they get shorted, means those wires are connected or touching, whether accidentally or consciously, whatever, but they end up touching. That is called as shorting. So shorting two things means connecting them. That's shorting. So in such a case, what will happen? Notice, very interesting thing. There will be current, but this current will be very huge. In fact, that current will be EMF by only one single resistance. Nothing else is there. One single voltage, one single resistance, that's all. So usually this is very, very small. That means this current is going to be very large. That means this cell will get discharged very quickly. So the cell discharges quickly. The cell discharges quickly. So if you do that for a long time, not even long time, decent time, that's it. All the energy is gone. This huge current is there, and a battery always has a capacity, you might have seen. So that capacity has some charge which it can deliver. All that current is given. The battery is gone. It's over. It has lost all its energy. So that is called shorting. And in case of shorting, you will notice the terminal voltage is going to be 0. Yeah. Because if you ask me what is V, this is just the voltage across a wire, if you notice. This and this, everything is a wire. So there is no resistance in between. So why would there be any voltage? So there is no voltage. There is no voltage difference and the current is going. That's it. It's lost, gone. All the energy is gone quickly. So that's a very interesting thing during shorting. So when you connect two wires and you short it, there is no voltage difference because you are connecting it. So that's what usually shorting means. I hope that doubt is also clear. Everyone understood? Awesome, 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 awesome. Yeah, come on guys, let's focus on the class, and there are some random students which usually come and mess up the channel, and these kind of students is the one which you should never ever bother about, because usually they are not students and sometimes they are students, but you know, they always like to show off some other channel which might be big and which is sometimes Hindi channel or something, and you know, this kind of issues usually come for other regional channels or English channels, because they are used to learning in Hindi, and then you come and see an English language channel or some other language, maybe Tamil or Telugu or you know, all the other beautiful languages that we have, and then you feel that no, this language is only better, that is not nice, oh you should learn in Hindi, oh you should learn in this is big. So guys, please, you are free to go anywhere you want. We are going to be very simple, focused, and you know, just going to deliver that quality content, that's all. So my advice to all those kids who are probably not even kids, who just want to put down some other channels, please don't waste your time here. The students who want to learn in English, you know what to do, and this is common. The reason why this channel exists is because of very few teachers, like-minded people who want to give this content to all those kids who want to learn English. So please focus. Okay, don't worry. Yeah, don't have to be sorry, man, for their bad attitude. I am happy that you guys know what is good and bad. So ignore that passing by crowd. Sometimes they are just competitors, or sometimes they are just sent by some people, or just they are very fond of some other teachers, and then they come and just disturb the class because they just don't like other languages. But we are not like that, man. We love all the languages, whether it is Hindi, whether it is Tamil, whether it is English. They are all our languages. It's just a medium of communication, and that's all. So don't have to take it so personally and create a ruckus out of it. Yeah, great. Moving on. So all the 4 things done: discharging, chemical to electrical work, voltage is lesser than EMF, charging where voltage is more than the EMF, and chemical gets stored from the external work. Open circuit, no change of energy, EMF is equal to voltage. Short circuiting, terminal voltage is 0, huge current, fast loss of energy. Great. Now let's learn how to connect these EMFs in different places, and getting those equivalent resistances, equivalent EMFs, etc. So just like we had resistors in series, something like this. R1, R2, Rn, and you can instead rewrite this whole set of resistances into a single resistance. That single resistance comes out to be R1 plus R2, like that till Rn. Whenever resistors are in series, the current flowing in all of them is the same. So it's the current which is same in all of them, but it is the voltage which is different and gets added up to the total voltage. So if this voltage is V1, this voltage is V2, this voltage is, let's say, Vn, you will notice that the total voltage across the net circuit is nothing but voltage additions across each resistance, like this. That is resistors in series. Similarly, you had resistors in parallel. Combination, meaning it branches out. Many resistance could be there, like this. This is R1, R2, R3, like that, Rn. Instead of all these resistors, you can replace them with one single resistor, something like this. Let's say this is R. So this reciprocals is what you should add. So 1 by the total resistance is 1 by R1 plus 1 by R2, like that till 1 by Rn. And in such a circuit, you will notice whatever total current enters within that circuit gets distributed in all the branches. So it's the current which is different. So current will be distributed I1 plus I2 plus, like that till In. But it is the voltage which is the same. So whatever voltage is there across any such resistor is the same voltage across every other resistor as well as the whole circuit. So the voltage is same across any such resistance. Correct? So this is something which you had learned in 10th standard. So it's kind of a quick revision so that you remember it. Now we are going to do the same thing but for batteries, and that is the main important formula. Okay. So what will happen if I have batteries connected one after the other in series or maybe even in parallel? So combination of cells. So when you have cells in series, meaning one cell here like this, next cell here like this, like that, there are n number of cells connected one after the other, E1 R1, E2 R2, En Rn. I can replace all these cells. Instead of all of them, I have one single cell with one single internal resistance. And the formula is very, very laddu. By the way, all these cells will have the same current, no doubt about it. So the current is going to be obviously the same. But what is the value of this effective EMF or effective resistance? Effective resistance formula is still the same. Whatever we had studied for series resistance, same thing is valid here also. So just chumma add all these resistances, internal resistance, R1 plus R2, like that till Rn. Just add all these internal resistance, you get the net effective resistance. No doubt about it. Okay. Unique Soul, I will ask the admin team. I don't know whether they will work in the night, but by tomorrow at least I will try to push it. Similarly, if you have cells in parallel, meaning something like this. There is a cell like this, then there is another cell like this. So many such cells are there. N number of cells are there. They are branching like that. This is E1, this is R1, this is En, this is Rn. Instead of all these cells, you could have one single cell and that will still do the job. That is called as the equivalent cell. And that will have equivalent EMF, equivalent internal resistance. That internal resistance still given by the same formula, just like you had for parallel circuits. So you will just write down 1 by R is equal to 1 by R1 plus 1 by R2, like that till 1 by Rn. That's all. It's the same thing. Yeah, one thing for sure, the voltages will be the same across all of them. It's the currents which will get distributed in these branches, as you can see. Right? Same logic as before, guys. The currents will obviously be distributed. If this is I1, this will be In, this will be I, this is also I. So current is I1 plus I2, like that till In. Currents will get distributed, unlike in series where currents would be the same. Fine, resistances are simple, sir. What about equivalent EMF? So for EMF, here is the logic. The answer is the EMFs for series just simply get added up. That's all. So it will be E1 plus E2 plus like that till En. That's all. Just simple pure addition, nothing else. Nothing else. And what about in parallel? Well, that's where the trick is. So when it is in parallel, the formula modifies to E1, observe this carefully, okay? E1 by R1. So I'll actually write it like this. 1 second, guys. EMF is equal to big denominator over here. And on the top, you will have E1 by R1, E2 by R2, E3 by R3, E4 by R4, like that till the last EMF by the last internal resistance. And then in the denominator again you have 1 by R1, 1 by R2, 1 by R3, like that till 1 by Rn. This is the formula. This is the formula. Correct. So both series and parallel, you should know both the formulas. Series is very simple. Just add the EMFs, add the resistance. For parallel, resistance you have already studied. Only the EMF is the next new thing that you have learned. E1 by R1, E2 by R2, E3 by R3, like that, divided by 1 by R1, 1 by R2, 1 by R3. Something like reciprocals only. Okay, but reciprocals are there, but with EMFs are there. So not very strange if you know resistors in parallel formula. So looks kind of similar, but there is numerator, denominator and all of it. Cool? Perfect. Hi Nayan, good evening. Yeah. आवाज नहीं आ रहा, क्या बोल रहे हो? आवाज is coming, man. The sound is coming. What are you saying? I can see the sound. It's coming. All right. What is the weightage of this chapter? Expect around 2 to 3 questions, not more than that. You have 25 questions, man. What weightage will I tell you? So, yeah, it is important. So, 2 questions usually come. Very, 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 very rare that 1 question will come. But it may happen in your shift. And again, very, very rare that 3 questions may come. So, that is the weightage. Okay. So, let's do questions now so that you will understand how to use this. Otherwise, these questions you will not be able to solve if you just by heart the formulas. Let's understand. There is a 7-volt battery with 1 ohm resistance and another 3-volt battery with 4 ohm resistance connected to a load of 15 ohm, connected to a load of 15 ohm. Question is, what is the current in this particular circuit? Okay, what is the current in this particular circuit? One easy way to do this kind of questions is get rid of both these cells. Instead of them, just write one single cell, one single EMF, and it is connected to this external resistance, which is still 15 ohms. How much is this EMF going to be? That EMF will be just the addition of these 2 cells. So it will be 7 plus 3, which is basically 10 volts. So this is going to be 10 volts. The total internal resistance, because they are in series, just will add. So 1 plus 4, which is 5 ohms. So now you just have to figure out how much current is there in this circuit. So that current will be EMF by external plus internal resistance. EMF is 10, external is 15, internal is 5. So it is 10 by 20, which is 1 by 2. That means the current is 0.5 amperes. That means the current is simply 0.5 amperes. Simple, easy peasy. Okay. Now let's take it up a notch higher. We'll take parallel so that you get the understanding of this formula. Let's say this battery is like this. Maybe this is 20 volts. Maybe this is 2 ohms. Then let's say this is 10 volts. And let's say this is 1 ohm. Okay. And we have been asked that can you figure out what will be its equivalent EMF, what will be its equivalent resistance, so that when I connect it to something, I can solve it easily. So fine, let's do it. So first of all, this will behave like one single cell, one single resistance. So if I want to find that EMF and resistance, the formulas goes like this. 1 by R is 1 by R1 plus 1 by R2. So 1 by R1 plus 1 by R2. So half plus 1 is 3 by 2. So that is 1 by R. Therefore, my small r will be 2 by 3 ohms. Okay, internal resistance is taken care of. What about EMF? EMF will be E1 by R1, that means 20 by 2, plus E2 by R2, that means 10 by 1, upon 1 by R1, that means 1 by 2, plus 1 by R2, that means 1 by 1. 20 by 2 is 10, 10 by 1 is also 10, half plus 1 is 3 by 2, 10 plus 10 is 20, divided by 3, that 2 goes on the top. So this will become 40 divided by 3, that is the EMF, because 22s are 40. So 40 by 3 volts is the equivalent and 2 by 3 ohms is the equivalent internal resistance. Simple? Okay. Now observe this. Observe this. Example. There are 10 cells of 3 volts and 1 ohm each in series. 2 cells are connected wrong with opposite terminals. What is the net EMF and internal resistance of the equivalent cell. Right? Very interesting. They are wrongly connected. They are incorrectly connected. What is the net EMF of that particular cell and the internal resistance? Now, I have seen a lot of people commit mistakes in this question. That is why I have taken this up. Let's think about it. I know what many people will do. They will take total resistances R1 plus R2 like that till R10. I agree. All the resistances are same, 1 plus 1 plus 1, 10 times. So obviously it will become 10 ohms. There is nothing wrong in it. This is perfectly fine. Nothing wrong in it. Internal resistance is totally 10 ohms. The problem happens for EMF now. Observe this. Many people I know, they will do this E1 plus E2 plus like this till E10, and they will be like, ah sir, we have 3 volts, so 3 plus 3 plus 3 plus 3, so 3 10s or 30s or 30 volts. This is not right, man. How can it be 30 volts? There are 2 cells which are wrongly connected. You did not use that information. Oh yes sir, you are right, you are right, you are right, you are right. Correct sir, correct. So it will be 3 plus 3 plus 3 like that. Sir, 2 batteries are wrongly connected. So from 30, sir, I will take out 6. So usually what I have seen people do, 2 cells are wrongly connected. So those 2 cells together will give 6 volts. So they will do minus 6 and they will give the answer as 24 volts. Now that is also wrong. Yeah, many people do this. I have known these mistakes. Many people are going to write 24 volts as the answer, but that is also wrong, guys. I'll tell you why. First, understand how many cells are correctly connected? 8 cells. So they will be 3 plus 3 plus 3 plus 3, 1, 2, 3, 4, 5, 6, 7, 8. Correct? 1, 2, 3, 4, 5, 6, 7, 8. 2 cells are wrongly connected, so they will give opposite EMF. So minus 3, minus 3. Now notice one interesting thing which happens. These 2 negatives cancel with these 2 positives. Obviously, they will end up cancelling out each other mathematically. So what is remaining is only this much part. Notice 1, 2, 3, 4, 5, 6. 3 6 are, it is just 18 volts. So it's not 24 volts, it is 18 volts. The mistake that you made mentally while calculating in your mind was you thought from total 6 volts will go. No, it's not from the total. It's from that 8 batteries total that the 6 volts will go. That is the mental calculation mistake you guys made. Understood? Understood, guys? Yeah. These are common mistakes. Awesome, my dear. Now, we can have another amazing example. You have okay, observe this very good example, guys. This kind of circuit was given. Let's say this is, I don't know, maybe 30 volts, maybe this is 3 ohms, maybe this is 10 volts, this is 1 ohm, maybe this is 2 ohm. This kind of circuit is given to you. Okay, it's a very interesting question, and the question says, can you figure out how much current is flowing, through the 2 ohm resistance? How much current is flowing through the 2 ohm resistance? All right, ready for it? Okay, ready for it, guys? Let's do. Now, at first, it feels like a complex question. Number 1. Number 2, students who have studied this entire chapter, they think we should use Kirchhoff's laws. Kirchhoff's voltage law, Kirchhoff's current law, they start making some equations and start solving it. Fine, we have not yet taught you Kirchhoff's laws, don't worry about it. The point is, you need not use any of these things, nor is it complicated. You just need to actually simplify it. So how do I simplify it? See, this is a resistance. Between these 2 points, there is a battery here, and between the same 2 points, there is another battery here. So between the same points, you have 2 sets of batteries connected side by side, parallel, guys. So actually speaking, the equivalent diagram, if I had to draw, I would draw it like this. There is this 2 ohm resistance, and notice how you have 2 branches. You have 2 branches over here. One branch is giving 30 volts to that 2 ohm with some resistance. You can term it as internal. I know it is outside, but think of it like internal. How does it matter? And the other cell, notice, a lot of people are going to do this mistake. They are going to write it like this. That is wrong. Observe carefully. This 30 volts is supplying the current this way, but this 10 volts is not supplying the same way. It is actually supplying the current the opposite way. Forget this for now. The 10 volts was supplying the current like this. So it's going in a very different way. Oh, 1 second guys, my board has got hung. Notice how this 30 volts is supplying the current like this, whereas this 10 volt is supplying the current like that. So it is opposite. So it is not connected actually in the same direction. How many of you are able to see this, guys? How many of you are able to see this? If you can see this, good. That was the catch. Number 2, the second catch was converting this complex circuit into a parallel circuit. Alright, let's do it. Just 1 second, guys. My board has got hung. Ayyo. So the real manner in which you should be connecting it is like this. Understood? So this is 10 volts and this is 1 ohm. Now these are 2 cells in parallel. So replace it with one single cell. Replace it with one single cell, one single internal resistance, and the same outside resistance of 2 ohms. That's all. This is EMF, this is the resistance, and now you can easily figure out how much current will be flowing. Got it? So for doing this problem, first we'll find the internal resistance using the formula 1 by R is 1 by R1, 1 by R2. So 1 by 1 plus 1 by 3, which is nothing but 4 by 3. So R will be 3 by 4. Okay. For finding the EMF, EMF will be E1 by R1. So 30 by 3. E2 by R2, which is 10 by 1. 1 by R1, which is 1 by 3. 1 by 1, which is 1 by R2. Now here is another catch. Because this battery is connected in the opposite manner, so 10 will not be 10, it will be negative 10. 30 is positive, but 10 is not positive, it is opposite. So please put minus here. Sir, should I put minus here also? No. Resistance is the same whether you go like this or like that. So don't put negative sign for resistances. This will be positive. Common mistake here is people put negative here also and they put negative here also. Resistances are not negative. EMFs can be negative because of the terminals, positive, negative. Sometimes people miss this negative sign, they put plus plus only. They forget this battery is opposite in the first place. Got it? So 30 by 3. Oh my gosh, something crazy is going to happen over here. 30 by 3 guys is 10 minus 10 and this is just going to be 4 by 3. Guys, it doesn't matter. 10 minus 10 is 0. Oh my god, the EMF is 0. You know what just happened? The EMF came out to be 0 volts. This came out to be 3 by 4 ohms. So what does this tell you about the current? By coincidence, just by coincidence because of the values which I have chosen, the current came out to be 0 amperes. So no current is flowing here. So then you might be wondering, sir, if no current is flowing there, where is that current going? What is it even doing, sir, over here? What is this circuit even doing? So the answer for that, just let's forget this for now. These calculations are done. What is really happening is if no current flows here, this branch is completely waste. There is no current here. So current has to go somewhere. So that current will start from 30, go like this, go like this, go like this. It can't enter here. So it will just go like this, go like this, go like this. It's just going in the outer periphery. It's just going in the outer periphery. Can you see that? Yeah, can you see that? It is just going in the outer periphery. Now for a moment, just forget the rest of the circuit. Just concentrate on the outer periphery. If you just concentrate on the outer periphery, you will realize this resistance, this cell, this resistance, it feels as if these two are in series. Even these two resistors are in series. So the equivalent resistance will be 1 plus 3, which is 4 ohms. These two supporting each other, 10 plus 30, which is 40 volts. So the current which flows in this part of the circuit, just the outer periphery, voltage by resistance, total resistance, voltage is 40, resistance is 4. So 10 amperes of current is just circulating on the outer periphery, nothing is coming inside. Understood? Is that absolutely clear? Isn't it a wonderful question, guys? Yeah. So to start off with, we saw how cells can be connected in series and parallel, and resistances also. The formulas look very nice, interesting, and we saw many questions when they are supporting each other, or even they are connected wrong manner, whether it is in series, or even this particular case where parallel circuits are there but they are opposing each other. So minus sign comes over here. So in this particular case, none of the current entered here. So by coincidence, it was just going in the outer periphery. It's a brilliant problem. Great. Cool. Let's say I do another question. The question goes like this. There are m cells of EMF E and internal resistance small r in series, and n such identical parallel branches connected to external load R. Find current in the load. Now such questions are given without diagrams. So to visualize it is the first task, and then to apply the formula without making silly mistake. That is the second. So let's understand the question. There are m cells of EMF E and internal resistance R. So imagine this is a cell, internal resistance, another cell, internal resistance. Like that, how many cells are there? M number of cells. E. Like that, if I label this as number 1, this will be 2, like that, this will be m number of cells. But there are n such parallel identical branches, meaning think there is one more branch with such cells like this. This is the second branch. Then there is a third branch, then fourth branch, and there is a nth branch, and there is a nth such branch. Crazy, right? So there are n such branches and they are all in parallel. That is what is making this question very interesting. They are all in parallel. So if I call this branch as number 1, this is number 2, number 3, like that. There is nth branch over here. They are n such branches. Now they are connected to an external load. So I take this and I connect it to some external load, and it is now connected over here. This is R. Question is, can you figure out how much current is flowing over here? So first, visualization. And I went really step by step in a systematic manner, so there is no confusion. M cells one after the other in series, n such identical branches together connected to a external load, finding the current. Okay, let's solve it step by step. First, if you consider any branch with m cells in series, can I not find the equivalent resistance? Equivalent resistors in series will be R plus R plus R, like that, m times, so it will become R into m. Equivalent EMF in series will become E plus E plus E, m times, so it will become E times of m. So instead of each branch with those multiple cells, what I can instead do, I can say, listen, there is only one cell, one resistance, one cell, one resistance, one cell, one equivalent resistance. This is exactly EM and RM, nothing else. This is E times of M, this is R times of M, E times of M, and this is R times of M. Like that, there are n such parallel branches. Okay. So if I now switch over to parallel, if I now want to convert all of these parallel into one single cell, I don't want any of these, I want to convert it into one single cell with one single internal resistance. This is EP, this is RP. How do I do that? Well, use the formula. 1 by RP will be 1 by R, 1 by R, 1 by R multiple times. So 1 by RM, 1 by RM. How many times it will come? Like that, n number of times. So won't it become n divided by RM? That is 1 by RP. Therefore, how much will RP be? It will be nothing but m times of R, the whole thing divided by n. That is the equivalent resistance internally, MR by N. So RP is nothing but MR divided by N. Perfect. Now let's talk about EMF. How much will this net EMF be? So the net EMF will be, let's figure it out, E1 by R1. E1 is EM by R1, which is RM, plus E2 is also EM divided by RM. Like that, n number of times, whole thing divided by 1 by RM, 1 by RM, like that, again n number of times. What will this become? Guys, can you see mm gets cancelled? Okay, forget mm getting cancelled. For now, just let me put EM by RM n number of times. Here also n number of times 1 by RM. Notice what is happening very quickly. RM got cancelled. Even this n got cancelled. Yes, I'm just getting EM. That's all, nothing else. So I'm just getting E multiplied by M. So the net EMF is just singular EMF into M. Perfect. Now this is a simple circuit. Finding the current is not a big task. So the current will be the total EMF by the total resistance, which is R plus RP. So total EMF was E multiplied by M. The total resistance will be R plus internal resistance, which was small mr divided by N. That is the value of the current. That's it. We have got the final answer. We have got the final answer. That's it. Nothing more has to be done. So this question clears literally almost all doubts, and you know how to use the formula, whether series, parallel, I mean all kinds of confusions go off. Khushi, I'm great. All right. Awesome. Awesome. Great. Love this question. Are you now little bit confident about series and parallel cells as well as resistors? Shall we go ahead? Shall we go ahead? Okay, very nice. Now you might see sometimes the resistors don't seem to be in series, don't seem to be in parallel so easily. So you might have to do some nonsense, manipulate, visualize, rearrange and bring it into a regular form. So let me show you those typical problems which you might get. Starting off with the first very common example, you might see a resistor here, a resistor here and a resistor here. You take this wire, connect it like this, you take this wire and connect it like this. This is R1, this is R2 and this is R3. Now the question is to find what is the equivalent resistance of this circuit. Now many people think, sir, aren't they in series? Well, they are not in series, my dear, because yes, it might look they are one after the other, but there are branches which are coming out and they are interconnected. So sir, should we think like this? Sir, the current, no, I know how it will come, sir. It told me in my dreams. It will come like this, it will go like this wire is there, sir. And then here it is getting confused, sir. So I think, sir, it will go here, sir. This wire is there, sir, and it will go like this. Bro, that is not how current will flow. Okay, because current, why will it go in this wire only? Why not in this resistance? Because if it goes in this resistance also, this wire is there. So it's not like it only goes through one path, there are multiple paths. Instead of doing all that nonsense, what you do is start marking all the same potential points, meaning see which are those points which are on a single wire, because a wire never has a voltage difference, same potential. So mark all those points, like for example this point, 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 this point. The moment a resistor comes, stops. Okay. Similarly, this point, 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 this point. All points same potential. Great. What do I do next? I can see there are only two kinds of points, two colors. Okay. So I will start off with, let's say, the pink point, and I can see that pink potential which is over here. It's connected to this resistance. It's going to this. It's also going to R3. So 1 point over here, 1 point over here, 1 point over here for each of those resistances. For R1, for R2, for R3. R1, R2 and R3. R1 has blue on the other side, R2 also has blue, R3 also has blue, and notice all the blues are eventually connected to a singular point. So the other terminal for each is this, and eventually they are all connected to another terminal over here. That's it. This is the actual equivalent circuit of this. I know they are just in parallel, guys. So simply put, the 1 by R equivalent will be 1 by R1 plus 1 by R2 plus 1 by R3, nothing else. They are just in parallel, nothing else. So usually such questions come. You might have seen for capacitors also this question has come. So one capacitor is there, one capacitor is there, one capacitor is there, C, 2C, 3C, and this is connected like this, this is connected like this. No worries at all. They are just, disguised. They are just manipulated, nothing else. So strictly speaking, they are just 3 capacitors in parallel. Just 3 capacitors in parallel, C, 2C and 3C. And when capacitors are in parallel, don't be fooled, don't take reciprocals. Yep, the C equivalent will be just addition, C plus 2C plus 3C, so it will become 6C. Got it? So in capacitances, remember the formulas are reversed. Series go to parallel, parallel go to series. So just add the capacitances when in parallel. In series, it is reciprocal. Okay. So This concept is even valid for resistors and for capacitors. Another good question of disguised. Another good question of disguised. Ready for it, guys? Everyone? Are you enjoying? Yes, no, yes, no, yes, no. Come on, everyone. Loving all these questions? Loving all these questions? Yes or no? Yes, sir. Perfecto, sir. I'm enjoying this question. Awesome, awesome, awesome. Okay, let's do one more question. All resistances R. Question is, find the equivalent resistance between the ends. Question is, find the equivalent resistance between the ends. You can extend this circuit to even more. So I have seen questions where there are multiple such things, and then you have to find, what is the equivalent resistance for this entire circuit. You can even have more number of squares also. Yeah. So doesn't matter how many ever squares you draw, solution method is still the same. Okay, it's just a manipulated diagram, nothing else. You just need to remove its disguise. It is disguised. Disguise means it feels it is something else, but it is not. It is actually simple. It is laddu. So this looks complex, but it is not complex actually. Okay, how do we do this? Think. Well, let's start marking our points which have the same voltage. Remember, on a wire, all points have same voltage. Okay, bro. So this point I start with. This is a wire I get. I go till here. I can in fact go here. I can go here. I can go here. Oh my God, this is crazy. And then I again start from the other side. And then I start seeing this point, this point, this point. In fact, even this point, even this point, even this point have the same voltage. Correct? Yes, sir. Another interesting thing, even this point, this point, this point, this point, this point, all same wires connected, interconnected, same voltage. Another interesting thing, this point, this point, this point, this point, this point, this point, all interconnected, same voltage. So you know what actually, if you start from the left side, which is the blue point, blue voltage, so it is actually connected to 1, 2, 3, 4. Oh, nice. So it is connected over here, and on the top I can see it is connected to 1, 2, 3. But out of that I can see these two resistors have yellow, these two resistors have pink. Okay, so I have an idea. So this goes maybe like this, maybe like this, maybe like this, like this. Okay, I tell you what I'm doing over here. This resistor as it is over here, this resistor as it is over here. Do you see on the other sides they are having this pink potential? So I just put pink. Just I'm using this color coding just to make you understand and visualize, nothing else. Otherwise I can do it in a very boring way. V1, V1, V2, 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 V3, 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 V4, V4, V4. So that is also fine, but I just wanted to make you visualize these things, nothing else. Okay, now these two blue things are connected to these yellows. So these two blue things are connected to these yellows. Okay, so together they are connected to basically these yellows, and these yellows are clubbed together. Interesting, they are clubbed together, and they are again connected to, can you see, two more resistors. This yellow is connected to two more resistors over here. Interesting, interesting. And those two resistors are connected to the greens which are connected over here. Oh my gosh. Oh my gosh. They are connected to the green values over here. Okay. Connected like this. And that green is again connected to two more resistors over here. My goodness, so many resistors like this, like this, like this. Can you see that, guys? Everyone? And these two resistors are connected to the pinks literally over here. Okay, perfect. Okay, and now this diagram feels complete. And now this diagram feels suddenly complete. Oh, now you can solve this. Now it does look like a simple series and parallel circuit, yes or no? Now it looks like a simple series and parallel circuit, yes or no, guys? So we have converted it into a simple circuit by analyzing which points have the same voltage. Here I have used colors, but in the exam you can't use sketch pens and colors. You can use boring numbers like A, B, 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 C, 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 D, 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 E, or V1, V2, V3, V4, V5, 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 V6, 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 V1, V1, V2, V2, like that. So it's up to you. You can mark the potentials anyhow. Now it looks simple, guys. Okay, fine. So what is these two resistors doing? Parallel. So parallel means effectively will be R by 2. These two are also parallel. That means it will again be R by 2. These two are in parallel. So again it will be R by 2. Then these two are in parallel. So again it is R by 2. Perfect. Okay. Like this, like this, like this. Now these three are in series. These three are in series. So R by 2, R by 2, R by 2. 3R by 2. So we have basically 3R by 2 and just another over here R by 2. So finally we'll convert it into a single resistor, the R equivalent. That R equivalent will be R1, R2 multiply with each other divided by R1 plus R2 after reciprocals and LCM. So it will be 3R by 2 into R by 2 divided by 3R by 2 plus R by 2. That's it. That's how you get it. Understood? So these kind of questions where you have to do manipulations, visualizations, rearrange and get the answer. Very, very common. You can get this for a triangle also, by the way. So you can draw a triangle also like this. Triangle inside a triangle inside a triangle. This kind of question is also there. Same concept, guys. Same concept they will use. Again, start marking the potentials and get the answer. So triangle, hexagon, quadrilateral, whatever you want. All these are same kind of questions. Okay, great. Now sometimes you might get infinite number of resistors. Okay, you might get not just one or two, infinite resistors. So then what do we do? Oh my god. So example, say this is 2 ohms, 1 ohm, and just this repeats and repeats and repeats. This is called as a ladder because it looks like a ladder, but a sleeping ladder. And there are many such resistances, you know, one after the other. This goes on infinitely. This is called as an infinite ladder. No finite resistances, infinite ladder. So how do I find such a resistance? Thank you, Ayush, so much. And by the way, I hope you guys know that very soon we are going to clear your backlogs. Shreyas Sir is going to help you out with not just backlogs, but also balancing your boards and JEE or any competitive exam. Plan according to your schedule and make your own personal schedule. So stay tuned with your Capto, and Shreyas Sir is going to help you out. We'll give you a proper strategy. We'll give you a proper tool to help you out. So video is coming soon. Okay, great. Oh, nice. We have Lakshya students also over here. Welcome, man. Welcome, welcome, my dear. Now, observe this. This is an infinite ladder. Okay. How do I find out the equivalent resistance? Now, the logic for such questions is infinities can't be compared, and infinity plus 1 is still an infinity. Okay. Infinity plus 1 is still an infinity. It is not that infinity plus 1 is more than infinity. Sir, there is one extra over here. So this infinity plus 1 is more than infinity. No, no, no. That is not how infinity is work. Infinity is not even a fixed number. It is a unimaginable number and you cannot compare two infinities. So infinity plus 1 is infinity. So if that is the concept over here, observe what I am going to do. I am going to say, for a moment, let's do one thing. Let's assume this whole resistance to be X. Assume this whole resistance to be X ohm, which is obviously the equivalent resistance which we have to find, which we don't know. Let's assume it. Cool, sir. Now what I am going to do is this ladder which is there, no? Infinite ladder. This infinite ladder. I will do one thing. Because you just said, sir, infinity plus 1 is still infinity. How about adding a one more pattern, repeating pattern to this infinity? So what I'm going to do, I'm going to add exactly one repeating pattern to this. So this is infinity and this is plus 1. It shouldn't make a difference. That means this whole resistance should still be X only. Because infinity is this is infinity plus 1 should still be infinity, meaning it should still have X ohms of resistance. Agree or disagree? This is still going to be X ohms. But sir, wait a minute. Out of this infinity plus 1, this infinity which is there, which you can see over here, that was already X, sir. Oh yeah, you are right. So can I just say, I can visualize this as this resistance as it is, this is as it is. This one thing which I put in orange is actually totally X ohms only. It is actually X ohms only. And this together is still going to be X. This together is also going to be X only. By the way, this is 2 ohms and this is 1 ohm. Now solving this circuit is not a big deal at all. And that's what our focus will be on. How to solve this circuit? Let's see. Let's forget everything else. I don't need anything now. This was just to make you visualize, guys. Otherwise, I will not be writing all these steps in the actual examination because you would have solved multiple questions on this. So I'll repeat what we did. We saw an infinite ladder and then we remembered the concept of infinity plus 1 being infinity. So I assumed this infinity as X. So to this infinity, I added one more pattern which got repeated. So that would still be having a total resistance of X only. There is no change. But out of that, I know this much part is having an equivalent of X ohms. So I replace this orange with X ohms and this equivalent is still going to be X. Now my focus is only on that, nothing else. I can see these two are in parallel. Guys. So you have 2 ohms over here, and this 1 and X are in parallel. So it will be 1 into X divided by 1 plus X because these two were in parallel. They were in parallel. Okay. Now I can see these both are in series. Can you see that? So I converted to this. Now I can see these both resistors are in series. So first step was that parallel. Now I can see series combination over here. So I can replace both these resistances with one single resistance. And what will that one single resistance be? X divided by 1 plus X plus 2. X divided by 1 plus X plus 2. Just add the resistance. But I know every single time I was doing it, there was X resistance together. Even this one totally is still X. So this is still going to be x ohms. Effectively, it is still x. There is no change in that. Correct? Very good. So now what do we do? Sir, if this is still remaining x, solve, man, mathematics, nothing else. You cannot sit and guess. So x is 5, sir, x is 2. Solve it. Nothing. It's an equation. Okay. Let's solve. What do we do? LCM, nothing else, man. What else can we do? X by 1 plus x plus 2 into 1 plus x, common denominator 1 plus x is equal to x. Take this 1 plus x, bro, on the other side. So x plus 2 plus 2x is equal to x into 1 plus x, which is x plus, wow, x square, my goodness, x plus 2x is 3x plus 2. Interesting. I feel I will shift it off to the other side. So 0 is equal to x square plus x minus 3x minus 2. Therefore, x square, x minus 3x is minus 2x minus 2 is equal to 0. It's obviously a quadratic equation. Yeah, it is a quadratic equation. So you are like, sir, are we doing it right? We are perfectly right, nothing wrong. You always expect a quadratic equation in infinite ladder questions. There is no other thing to do but just to solve this using normal quadratic rules, guys. So x will be minus b, which is 2, plus or minus b square minus 4ac, two roots of this equation. B square is 4, minus 4 into a is 1 into c is minus 2. So this becomes plus, whole thing divided by 2 into a, which is 1. Okay. So this will become 2 plus minus the whole thing divided by 2. 4 2s are 8, 8 plus 4, 12, root 12, root 12, root 12, root 12, 4 into 3. So 4 into 3 means 2 root 3. Okay, so 2 to 2 gets cancelled. So it will become 1 plus minus root 3. But I'm not very happy about it because there is a negative sign and positive sign. I might have to make a choice. Now when I do 1 plus root 3, I'm fine with it. But when I do 1 minus root 3 is 1.732, which is more than 1. So when I subtract 1 with 1.732, it will make it negative. So that's what makes me unhappy. So I will ignore it conveniently and I will just say x is equal to 1 plus root 3 ohms. That's all. So I'll mention this point over here. 1 minus root 3 is negative resistance. Negative resistance doesn't make sense. It is not possible only. So ignore it. See, maths might tell me anything, but whether to take it or not take it, it's up to me. Got it? So maths just got an equation. It started solving it and I was like, okay, bro, you get two values. But out of those two values, what makes sense? That you have to think. That is why physics is there. Everyone, fine till this point? So infinite ladder questions, you will get most likely a quadratic equation. Perfect. Loving it. So many questions. I hope you are getting deeper, involved, and more confident, more knowledgeable, everything as this lecture is progressing. It's a proper lecture, guys, for all the students who want to crack JEE. Moving on. We did series parallel. We saw series parallel of cells. We solved infinite ladder. We solved disguised problems, also manipulations. Now, imagine the question is neither in series nor in parallel. Okay. It is something else only. It is something weird only. Then you are stuck. You can't use any of the series parallel formulas. So that's when the next two rules come, and that is basically, oops, my God, there are big mosquitoes. From where it came? So the next rule, the next law, the next theorem which helps me is Kirchhoff's laws. They help me solve any complex circuit. You have any complex circuit, whatever is that complex circuit, doesn't matter. You use Kirchhoff's rules, Kirchhoff's laws, then you make it into a very simple circuit. You make it into a very simple circuit. That means you can find the equivalent or you can solve it very easily. That is the whole purpose of Kirchhoff's laws. Sir, is this so magical? Yes, it is magical, but when things are looking so easy, the procedure is usually difficult. And that is the only big turn off, I would say, about Kirchhoff's laws. Okay, so it is just procedural, it is just probably lengthy at times, but otherwise it helps you solve problems. So expect few questions from Kirchhoff's law, but not very lengthy in mains, but sometimes lengthy in advanced. So let's understand what these laws are. The first law is all about the currents. If you have a junction or a node means junction where all wires are connected, or 2 wires or 3 wires or 4 wires, maybe some wires are connected. So there is a wire here which is connected, another wire coming here is connected, another wire, another wire, another wire. So that is basically a node. And in these wires there might be some currents with some different directions, I1, I2, I3, I4, I5, like that. Okay, some currents are either going in, some currents are going out. This first law, which is called as the Kirchhoff's current law, KCL, Kirchhoff's current law. This is based on conservation of charge. Conservation of charge, and it is applied to a junction or a node which is a collection of wires. It says that, simply put, whatever total current enters inside will be the total current which exits out of that particular node. Simply put, that is Kirchhoff's current law. And the reason why it is valid is because if it were not true, think otherwise. Imagine there is a junction. 5 amperes current is going in, but what is going out is 7 amperes. Who gave that extra 2 amperes? Nobody. Imagine if only 3 amperes is going out. Then how is it that 5 is going in, 3 is coming out? Where did that 2 go? It can't go anywhere. So charge has to be conserved. Whatever goes in has to come out. So whatever current enters inside should be the current going outside. Now if you look at this diagram, currents going in are I1, and then you have I2, I3 is also going in. Yes, I3 is also going in, but I1 is going in, I2 is going in, I3 is going in, even I5 is going in. I5 is going in. But which is the current which is going out? I can see only one current which is going out, which is basically I4. So I4 which is going out is I5 plus I2 plus I1 plus I3. Got it? So that is Kirchhoff's current law, nothing else. Great. Everybody understanding till this point? Cool? Very good. Next, the second law is Kirchhoff's voltage law. Now, to explain that Kirchhoff's voltage law, let me take an example of some mountains. Okay, there are some mountains around you, and we know the earth is round, and let's say there are mountains around you. The earth is full of mountains, and what happens is you are over here, you start going on those mountains, you are on a journey around the world. So sometimes you will go up plus 2 meters, then you will go down minus 3 meters, then again you might go up maybe 4 meters, again you might go up, again you might come down, again you might come down, again you might come down, like that. But if you add all these numbers, because you are eventually coming back, you came back. If you add all these things, what will that sum come out to be? Obviously 0 meters. Because whatever you went up by, you came down by the same amount eventually, and that's why your net difference in the heights because you returned is 0. Is that right? Correct? Understood? Now the same logic is applicable for electricity, but instead of going up or coming down, think of increasing the voltage or decreasing the voltage, raising the bar of voltage or lowering the bar of voltage somehow. So you go in a circuit and you encounter an increase in the voltage, surge, and then you go through something else, you might reduce the voltage, you might drop the voltage. Again you might go into something, there might be a increase in the voltage. Again you go into something, there might be a drop in the voltage. But eventually, if you somehow come back to the original place, whatever the voltage was increased by, exactly the amount of decrease will be the same. So if you add all these increases and decreases with the proper sign convention, the total sum should be 0. Does that make sense to all of you? Does that make sense to all of you? Yes? Perfect. So the same logic is applicable for electrical circuits. So if I have a complex electrical circuit like so, okay, so this is some electrical circuit, guys, okay, and you start from a point, you start from this point and you also end at the same point, you start going in that circuit, you start encountering devices, you go across the circuit and you complete this loop. This is called as a loop. This is called, what is this called? This is called as a loop. You will see the total voltages across all the devices that you get will always be a big fat 0. This is called Kirchhoff's voltage law. Kirchhoff's voltage law, KVL. Now this is based on energy principle, based on energy conservation. Kind of makes sense because whatever increase will happen will decrease and eventually are coming back, so it is conservative, so you know it will maintain that voltage. Just like you going up and down, you are increasing, decreasing, you are conserving your height eventually because you came back to the same point. So the height should remain the same. Same means conserved, means constant. Same way you came back to the same point, so it should be conserved, the voltage, energy, so based on energy conservation. Alright, so change in the voltage across a complete loop is always 0. This is very, very important, across a loop. Now sir, how do I know whether the voltage is positive or negative? I'll give you a simple example. I'll give you simple example, and this is very, very important, the sign convention of it. Let's say we have a resistance of 5 ohms and let's say there is a current of 2 amperes, my dear. Okay. Now imagine you are going in a circuit and you are getting that resistance somewhere in between. So while traveling, let's say I am going from here to here. This is how I am traveling. I'm traveling like this. This is how I'm traveling. Okay. Now, how much voltage drop will I get magnitude wise? I'll use Ohm's law. Sir, voltage across the resistance is IR, sir. What are you even saying? Yes, you are right. So it will be 2 amperes into 5 ohms. So that will be nothing but 10 volts. But sir, how do I know whether it is positive or negative? Bro, that is simple. Because in a resistor, current always goes from high voltage to low voltage. So strictly speaking, this is higher voltage and this is lower voltage. So what do you mean, sir, over here? Come on, now it's obvious. If you are going from high voltage to low voltage, what does it mean? You are dropping your voltage. So you are already at high, you have come down by 10 volts. So hence the answer is negative 10. That's it. So if you travel in the direction of current, the drop is IR. The drop is IR, so it will decrease. But if you happen to go like this, if you are traveling like this, if you are traveling like this, if you are traveling like this, still drop is IR only, which is 2 into 5, which is 10. But this time it is positive because you are going from low to high, you are climbing up. So all you need to do is think whether you climb up or you climb down. If you understand that, it is becoming easy. Mustafa, 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 don't worry, Mustafa, hum hai tumhare Mustafa. Day by day, rules birthday, friendship K. This is a very famous song, man. I love this name and love this song too. Mustafa, how can I be in two places at the same time, bro? Unless I'm a Schrodinger cat or Schrodinger Shreyas Sir. Quantum mechanics is not going on. Similarly, let's take a battery. Let's take a battery. Let's say this is some volts battery, 7 volt, chumma I have taken. And while you are traveling in that circuit, you encounter a battery somewhere and it is like this. So let's say I end up traveling like this. I'm going like this, I'm going like this, I'm going like this. I'm going from the positive terminal to the negative terminal, high to low. So that's it, it's a drop. But how much? 7 volts, that's the terminal difference, that's it. So answer is 7 volts but negative 7. Higher to lower, simple. Got it? हाँ लगाओ ईशान, जो लगाना है लगाओ, बॉट अटैक लगाओ, पाकिस्तान अटैक लगाओ, न्यूक्लियर अटैक लगाओ, whatever attack you want to put, you attack, man, attack, kill off everybody, everything you kill off. Okay, awesome, awesome. I can guide you, sir. Where you want to guide me? I'm MBBS. What happened to me, Tilak? I'm fine only. Don't scare me like that. I am MBBS students. I can guide you. Means I get scared if MBBS student says like this because you are future doctors. Then I will start thinking what is wrong with my health. Don't say such things. I will get scared. Oh my god, you guys are so funny, man. Looking at your chats, it's really entertaining sometimes. Sometimes I really feel you guys really don't know, or you are really too innocent, or you are really genuinely asking or just mocking. I don't know. Sometimes looking at your chats. Anyways, coming back over here, from this side to this side, what will happen? What will happen? What will happen? You are going from the negative side to the positive side. No. So obviously the voltage will increase and it will be plus 7 volts. Got it? So that's the simple way of looking at sign convention. Let me also talk about capacitors. So imagine this is a capacitor. Let's take something here. Let's say this is, I don't know, 2 farad and maybe some, I don't know, 10 coulombs of charges there. Maybe this is the positive plate, this is the negative plate. So if while traveling in the circuit, you go across the capacitor like this, you go across the capacitor like this. Look at it, you are going from positive side to the negative side. So there will be a drop of the voltage, so it will be negative. But had you traveled like this, clearly there would be an increase, positive, minus to plus. How much will be the change? Q is CV. Do you remember this formula? Q is equal to CV. So V will be Q divided by C. So that's it. That is the formula that you are going to use to find the voltage difference. Q by C. Q is 10, C is 2. 10 by 2, which means it is minus 5 volts. If you go from here to here, it is positive. 10 divided by 2, Q by C, which is again plus 5 volts. Got it? So that's how you can find voltages across any such combination. Very nice. Amazing. Sir, I will teach you how to live life for free. Thank you, Jasmine, so much for telling me how to live life for free. If you please find that, please tell me, because right now Shreyas Sir is paying so much taxes. To live life, we have to collect food, you know. So living life is not for free, unfortunately for me. So if you really have a way to tell me how to live life for free, please tell me. I would be very, very happy and excited, and probably we can share this knowledge to many other people also. I'll make a video also on it, how to live life for free. Because I thought people pay taxes, people have to pay for food, people have to pay for a house, people have to pay for literally everything to stay and live, and you know. But if you look at animals, on the other hand, they live for free. Nobody saw hippopotamus pay some money to buy some food. It just goes and just eats that plant. Or maybe even a, I don't know, a monkey just climbs the tree and eats the fruit. No, that's it. It lives for free. Humans, very weird, isn't it? We have to pay to live. Crazy. We have to give exams apparently. I don't know. Why is this? So if you have that solution, please tell me. We should probably change the nature of how humans live. Okay. So let's have a look at another kind of question. Let's say you have a question like this. This kind of questions are also very interesting, where you need to use the concept of sign conventions which you learn in Kirchhoff's laws, but it is a partial Kirchhoff's law problem. So there is an incomplete circuit given over here. They give you the potential of some random point somewhere. Some values, some current, something is given, or you are finding it out. And some random other point is there, and you have to find the voltage at that other point. So how to do such a problem? So I will tell you. Okay. How to do this? How to do this? All right. So my dear warriors, here is the logic. You start at a point, let's say, which you know already, which is 40 volts. Start moving towards that unknown point. On your way to that unknown point, you will encounter different devices, isn't it? And each device will either raise the voltage or drop the voltage. Write down all those values. Okay, I had 40 rupees. One place I got 2 rupees. Other place I had to give 5 rupees. Other place I received 7 rupees. Other place I gave 10 rupees. So eventually I'll be left with some balance amount in terms of voltage. So whatever is remaining is that final voltage. That's the simple logic. So what is it? Start from the known point, start traveling towards the unknown point, find your way through the circuit. On your way, you will encounter devices with raising or dropping those voltages. Add them up to the original value. That's it. You're going to get the answer. So V0 will be starting voltage wherever you have starting plus delta V across all the devices that you encounter along the path that you travel. So when I started, the voltage was 40 volts. The first device that I have encountered is the resistance, but I am traveling in the direction of the resistance, and I saw current when it flows in the resistance, then it goes from high to low. That means I am dropping the voltage, so there will be a negative contribution from that resistance. Negative contribution from that resistance. So it will be negative IR. I is 2, R is 3. Do you understand why IR with negative sign is there? This is high voltage, this is low voltage. So I'm dropping that voltage by 6 volts. Perfect. Perfect. So next thing, I am encountering a battery. When I am going in a battery, this is high, this is low. Oh, again I am going from high to low. My God. So over here, there is a drop of that voltage from high to low of just 10 volts. I think I forgot to, what is this? Put signs over here, minus plus. Okay, perfect. Minus and plus. Okay, perfect. What now? Next, capacitor. I'm going from minus to plus. So increasing. I'm climbing up. So when I'm climbing up, positive. Q by C is the voltage, standard formula. Q is 20, capacitance is 2. And when I add all these numbers together, I have reached finally over here. That is the voltage at that particular point. So it will be 40 minus 6 minus 10 plus 10. Plus 10 minus 10 cancels. So 40 minus 6, that's going to be 34 volts. So that's the answer at this place, V0. Got it? Everybody? Okay, this formula I didn't know. Now you know, right? At least. Now I'm telling you. This kind of formula is there everywhere, many times. Okay, so this is called as Kirchhoff's voltage law, where you add up the voltages across those devices which you meet on the way. If you return back to the same point, then your voltage difference is 0. But if you land up at some other point, then you will get the voltage at that point. So that is how it works. So if you start somewhere and you go somewhere else, if this is the start and this is the end, then the potential difference in the end will be potential at the start plus sum of all the voltages that you get on the way, basically on the path that you travel. See, this is a special case of this because your start and end is the same. So what happens? These both will cancel. That is why the total voltage comes out to be 0. So think of it as this being the general case. This is a very special case of this formula. Okay. So this formula is also kind of useful at times. But this is not for a complete path. This is only for an incomplete path. Great. Sir, show me how do I use this? Alright. Show me how am I going to use this. Ready for it, guys? Shall we do some question where we have to actually use Kirchhoff's voltage law? We have to use Kirchhoff's voltage law. Okay. And we have to figure out what is probably the equivalent resistance or something like that. Okay. We have to find what is the equivalent resistance or something like that. Ready, everyone? Paka? Shall we start? Awesome. Come on. Show some josh, show some energy in the chats. Let's take a good example and maybe of a cube because this is a very, very good example, guys. You have a cube. And every side on the cube is a resistance. Every side on the cube is a resistance. This, all resistances are equal. Lot of resistances. All these are anything else? Yeah, here. All these are resistances. And you have to find what is the equivalent resistance. What is the equivalent resistance of this particular circuit? Interesting. Let's try this out. Now, at first it looks like a good question, easy question, sir, cube, something interesting, sir, visual, sir. But then you realize you are in a mess. You realize you are in a soup. You realize you have probably misjudged the level of difficulty of the problem. Because none of these resistors are either in series nor even in parallel. Okay. So you cannot do this problem by simple series or parallel circuit. Okay. So what do we do now? in such questions, when you have to find equivalent resistance, do one thing. Connect it to some power source. Let's say I call it V, some random power source. And I know for a fact that eventually what I want is, yes, this power source is still there. I just want a single resistance, which I am calling it as Req, or you can call it X, whatever you want to call it. And when that happens, I know that whatever current is there in this is also the current in this. Yes, correct? So eventually it will convert it into a single resistance, and I know whatever current will be given here will be the same current here. Yes, sir, correct. But now, how exactly is this current going to travel? That is the next point. Okay, this current comes, it starts entering this cube. Now I want you to visualize, because the same current is also going to leave that cube. Visualize there is a body diagonal from this vertex to this vertex. Visualize this in 3D. There is a body diagonal. Visualize this in 3 dimensions. So as soon as you enter, there are 3 ways, 3 routes, 1, 2 and 3. And when you leave also, there are 3 places from which it merges, 1, 2 and 3. And guess what? All the 3 are identical. All the 3 are identical. All the 3 are identical, because look at it, when you enter over here, whether you go like this or like this or like this, visualize this. After entering over here, whether you go like this or like this or like this, you are still going to encounter 2 resistance ahead. Here also you are going to encounter 2 resistances ahead. Here also you are going to encounter 2 resistances ahead, which eventually merge to a single wire, which eventually you can see they will again merge to that single wire. So it doesn't matter which route you take, you are seeing they are all identical, because eventually they are splitting, diverging, merging exactly the same way. So if I go via this route, yes, it splits into these 2, again merges into these 2 and comes out from here. Check this out. This is one way of going. Another way of going, you go from here, it splits into these 2 and then merges into these 2 and then comes out from here. This is another route that you can take. If you go like this, you split into these 2 and merge into these 2 over here and come out like that. So no matter which route you take from here, this or this, so all these 3 are identical. The same logic also applies over here. This and this, all the 3 merging points are identical. So if they are identical, there is no difference between them. So current will also not differentiate between them. Yeah, it is impartial. So obviously the current has to get divided equally. Do you agree with this point? I by 3, I by 3, I by 3. Same thing over here, I by 3, I by 3 and I by 3. Make sense? Great. Perfect. Now if that is the scenario, what happens next is even more interesting. After the current splits into 3 parts, what happens at the next 3 points? Next 3 points. Notice, they will again split into 2 parts. So after reaching here, it is splitting into 2. After reaching here, it is splitting into 2. After reaching here, it is again splitting into 2. Yeah. And both those splits are equal, because after splitting into 2, it is again merging back over here. After splitting into 2, it is again merging over here. After splitting into 2, it is again merging over here. Oh, so after each of these I by 3 currents reach another junction, they are splitting into 2 parts every single place, and they will be I by 6 and I by 6, half. I by 6 and I by 6 will make it I by 3. And again you can see over here, after it splits into I by 6 and I by 6, it again comes back over here. Perfect. So now I have got a complete picture of how exactly the currents are traveling. So let me start marking it. This will have current of I by 3. This will also have I by 3. This will also have I by 3. This will also have I by 3. I by 3. I by 3. This will be I by 6. This will be also 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 I by 6. These are the splittings of those currents. Once I get to know how the currents are exactly split, that's it, my job is done. Now, the problem is almost done. Next 2-3 lines only you are going to get the answer. Yeah, 2-3 lines only we are going to get the answer. How? Observe. You choose a loop. Go from a path of your convenience. Start from the same point but come back to the same point. Let's say I start from here. I go across this and I have multiple options to go, but I have to come back to the same point. This is one option. Somebody will say, no sir, I will start from this. I will go like this, I'll go like this, and then come like that. Yeah, you can do that, quite lengthy I feel. Somebody will say, no sir, I will just choose a very easy way and I'll come like this. I think that is a smart move. Choose a convenient path. Choose a convenient path for travel. So I will start from this point. Probably I'll go like this, go like this, go like this, and come back. So this is my closed path. Closed path starting from this point. Starting from this point. So let's start from this point, choosing a closed path and use Kirchhoff's voltage law. Kirchhoff's voltage law. That's it. First thing I encounter is a battery. I am going from lower terminal to the higher terminal. Low to high, it's a jump. So it will be having a plus V voltage. Keep going, keep going, keep going, keep going, keep going, and going like this. Oh, I'm encountering a resistance, but I'm going in the direction of the current. Notice how the current is flowing. It's splitting like this, going like this, right? So I'm going in the direction of the current. So there is a drop in the voltage and it will be current into resistance. Current is I by 3, resistance is R. Correct. I continue. Oh, I encounter a resistance again. So there is a drop because I'm going in the direction of the current. In the direction, voltage drops. I by 6 into R. Continue. Oh, again a current with a resistance. So I by 3 into R. Continue. Nothing. And I came back. Okay. So this should add up to be 0. Correct? In place of resistance, if you do it for capacitors, it will still be the same process. No difference at all. Okay? No difference at all. Okay. V. Now what is this? I by 3, I by 3, I by 6. Okay, we'll all shift it to the other side. So IR is there, man. 1 by 3 plus 1 by 3 plus 1 by 6. So this will become IR. LCM bro is 6. So 2 plus 2 plus 1. 4 plus 1 is 5. So it will become I into R multiplied by 5 divided by 6. What, sir? What did you achieve doing all of this? For this you did it. What will I do with this now? What are you going to do? Tell me. Okay, I'll tell you what I'm going to do. I'll come back a little bit. Remember, this was our whole objective. If I wrote what is this voltage, current and R equivalent, what would you write? V is equal to I into R equivalent. Isn't it? That's what I would write. V is I R equivalent. Now you will understand why I did all of this nonsense. Compare this with V is equal to I into R equivalent. Your job is done. V is I into R equivalent. That's it. Your job is done, man. What else? So your equivalent resistance It's just 5R/6. Job is done. Perfect. That's it. So that's how you can use Kirchhoff's voltage laws, Kirchhoff's current laws to figure out the equivalent resistance when you feel nothing is working out and you feel none of them are in series or in parallel. So it makes the job not easier, but solvable. It's definitely not small, but it is definitely solvable. Why there is no series or parallel? Tell me. In series, there should be no splitting. Do you think this and this resistors are in series or these three? No, because what is happening? The current is getting split. Same current is not flowing. So they are not in series. Nor are these three in parallel because this point, and this point, they are three different points. So they are not in series, they are not even in parallel. Making sense now? Okay. So this kind of questions also you might get. But I'll tell you something. Most of the times, I'll tell you, see, the funny thing is, JEE teaches you some complex rules and you are expected to avoid those long procedures at times to make the problems easier. So usually what happens is students always try to, or even teachers, it's natural, try to think of ways to avoid Kirchhoff's laws only for the fact that it is very tedious, very boring, just a procedure which you need to solve. Apart from the fact that some questions might involve some nice diagrams, some visualizations, some 3D, some symmetry and all of that. Except for that part, this process is quite boring. So usually we will try to figure out ways in which we can avoid Kirchhoff's laws. So we'll always try to see whether can I make it into series parallel? Is it actually a simple circuit? That will be my whole purpose. And one such question is a question of symmetry. You might get multiple questions where there is some complex circuit. This is the entry, this is the exit, and you will have to find the equivalent resistance. And what happens is, if you join the line between the 2 points where you have to find the equivalent resistance, this is one point, this is the other point, this is a line which joins those 2 points, this is the line joining the terminals for finding out R equivalent. Now the next step is drop a perpendicular bisector to it. Drop a perpendicular bisector to such a circuit. Okay, fine, we'll drop a perpendicular bisector. This is a perpendicular bisector to that circuit. Now is the next interesting thing. On that perpendicular bisector, you might get anything. Maybe you might get some device, you might get some another device, whatever, alright, doesn't matter. All the points on that perpendicular bisector, all the points, all these points, they have same potential. All points have same potential. If they have the same potential, by the way, why do they have the same potential? Because of this perpendicular bisector, nothing else. And this is a symmetry. This is a question where symmetry exists. So whatever is there on the left side is there on the right side. So there is a kind of symmetry which is there on left and right. So left-right symmetry or whatever, front-back symmetry, whatever you want to call it. Left-right symmetry. Now please don't tell me, sir, the circuit came like this, sir. I was looking at left-right, then I understood I had to look it like this. So there was top-down symmetry, but in the notes you get left-right. So think logically, guys. I'm referring to, from the terminals perspective, left to right, there is some kind of symmetry over here. Whatever is there on the left, same identical thing is there on the right. Because they are identical, That is why all these voltages are equal on the perpendicular bisector. Because imagine if I assume this volts as 0, then naturally this will be plus 5, this will be, let's say, minus 5. Because they are symmetrical, the voltages will drop exactly the same way. So this is the exact midpoint of that entire circuit. Okay, no matter from where you look at it. And the moment all the voltages are equal, there is no voltage difference on the perpendicular bisector. On the perpendicular bisector. So that means if there is no voltage difference anywhere on that perpendicular bisector, it's as good as useless. It's as good as no current which is going through it. So basically you can just ignore the elements. You can ignore the elements altogether. You can ignore the elements altogether. That's all. So if there is some device, on that perpendicular bisector, just ignore it, man. That's it. Just ignore it and just think as if this terminal is there, this terminal is there. So it's like this, okay? Just imagine. Just forget that device is even existing. Completely ignored. Ignore. Nothing is there. Ignore. That's it. Sometimes you might not see a device, you might see a junction. That is also quite likely, something like this. So if there is no device but a junction, then you just split that junction like this. Make it look like a device, just like over here, and completely remove whatever was there. You disconnect it. Remove or disconnect it. Sometimes it is called as connection removal method in some books, disconnection method. These are all the same things. So whenever you see a perpendicular bisector like this forming symmetry, if there is a device, ignore that device. If you see a junction or a node or a joint, just make it look like a device. Just open up that joint and remove that joint, disconnect that joint. That's it, from top and bottom. Okay, cool. That's the logic. So let me show you an example so that you understand how to use this, how to solve these questions. So I'm just going to show how to apply it. We are not going to solve the entire question as such. Okay, this is just to make you understand how to use these concepts. Resistor, 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 resistor. This is one of the most important problem. Now, if you notice in this particular question, there is definitely a kind of symmetry, and what you do is join the 2 points where you want to find the equivalent resistance. Perfect. That is that yellow line. Now I draw a perpendicular bisector. Yes, I see a perpendicular bisector. Whatever is there on the left is there on the right. So this is your, so basically this becomes your line of symmetry. Line of symmetry. Whatever is there on the left is there on the right. Perfect. So anything which is there on the line, vertically ignore it, not horizontally. So people will be like, sir, should I ignore this resistance? No, 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 no. It is not vertical. It should be on that line. So I cannot see anything apart from that joint over there. So if you notice, there is a joint on that line. There is a joint on that line. What did I tell you about joints? Just open it up. Just open it up, man. That's it. Just open up that joint, disconnect it. This is the exact way of doing it. So disconnect that joint. Disconnect that joint. Job is done. All right. Disconnect that joint. So the simplified diagram of this would be, if you disconnect the joint, this resistance, this resistance, this resistance, this resistance, okay, this, oops, this resistance, okay, this resistance, this is disconnected, this is there, okay, perfect. That's it. That is the simplified version after I have used my concept of connection removal or symmetry, whatever you want to call, you can call it. Is that right? Very good. Now this looks very easy. How? Sir, these two are in series, correct? These two are in parallel, these two are in series, and this entire thing is also in series. So now it looks very easy to solve. Now you can solve it, isn't it? So slowly you start reducing the circuit. So this will then become like this, then like this, and then this will be one single thing. Then next, after this, reduce that also. These two are in parallel, so connect it into one single thing. That's it. And then this. Now these three are in series, so convert it into one single resistance, and it is in parallel with this. Now these two are in parallel, so you will easily be able to do it. So that's how you can start reducing the circuit. Got it? Step by step we have done it. Step by step. Clear? Yeah. In fact, this is something like Wheatstones. Yeah, you can say that. So, but without the Wheatstones. Okay. So, in fact, there is this beautiful problem of cube also using the same concept of symmetry. But this time, the terminals are slightly different here and here. You have to find what is the equivalent resistance. Guess what? The same question can be solved by symmetry again. Use the same logic. There is a symmetry, and tell you how. These are the 2 points across which you want to find the equivalent resistance. This is one vertex, this is the other vertex. Drop a perpendicular bisector to it. Perpendicular bisector to it will be like this. Visualize this in 3D. But that perpendicular bisector is no longer a line. I feel we should make it as a plane, guys. Yeah, it's not just a line. Visualize that. There's actually a plane which is being formed. Yes, that is the most important thing of this problem. So this plane that you see is the plane of symmetry. This is that plane of symmetry, and you can see whatever is there on the right side is there on the left side. Can you see that? Symmetry is existing. Symmetry is existing. Visualize this in 3D. All the points on that plane of symmetry are at the same voltage, meaning this point, this point, this point, this point have same potentials, So if there is anything which is connected between them, best to ignore it. No point showing it. There is anyways nothing going through it. So just leave it, man. Don't worry about it. Okay, cool. So let me think, how will it look? Let me redraw. Okay, let me just redraw and see what will it look like. Observe. Between these two, I see there is this edge. So I think we should ignore that edge. No point showing that edge. Between these two, there is nothing. Ignore. So there is one more thing over here. So I think I can ignore that also. That's it. And these are the two terminals. Now, this is my complete diagram. Can you see that, guys? Yeah, I have ignored, I have disconnected because their potentials were same. Look at that. This point and this point, same potential, so ignored. This point and this point, same potential, so ignored. Now, guess what? This is actually a simple series and parallel circuit. Yes, it is a simple series and parallel circuit. I'll tell you how. These two are in series, these two are in series, and their combination is in parallel. So, actually speaking, same thing is even valid over here. So, if I may, one resistor here, these two in series, these two in series will make it 2R. These two in series, this one and this one, will also make it 2R. They are combined together. This is one single resistance, okay, R. These two in series is 2R. These two in series is also 2R. Can you see that? So I have converted into simple series parallel circuit, nothing else. Keep converting it till you get one single resistance, nothing else. 2R and 2R is just R. So this is R. 2R and 2R in parallel, that is just going to be R. This is just going to be R. These two 2Rs is just going to be R, guys. That's it. Perfect. Now these three R's are obviously in series. So it will become 3R. And this is over here just as it is. Now we can see, yep, we got our final answer. A single resistance parallel, right? So R into 3R divided by R plus 3R. So that will be 3R divided by 4. That is the answer. So we can solve these kind of circuits also. 3R by 4. Understood? So symmetry problems are also very, very popular. Now, since we are talking so much about symmetry, it's also a good time to talk about something called as Wheatstone's bridge. Wheatstone bridge. And that is also a very useful kind of a question. Basically, you have this is even valid for capacitors, by the way. So let's say this is R1, let's say this is R2, let's say this is R3, let's say this is R4, let's say this is R5, some voltage. Now, same concept, similar concept of symmetry, but need not be exactly symmetrical. See, if any two points have same voltage for some reason, no current will flow through it, so there is no point showing such a device. Now, imagine this point over here and this point over here by chance have the same voltage, let's say V1. So if they are same voltage, so there is no voltage difference across them, and if there is no voltage difference across them, through this resistor there will be no current. So it is as good as useless. It's as good as useless resistance. So I can completely ignore that resistance R5. So the simplified version of the circuit will just have this and this over here with this battery, of course. That's it. We have completely ignored whatever was there in between. So it becomes now a simple series and parallel circuit. Otherwise it was not. Now when will this happen? This will happen only under a particular condition when this and this and this are in the same ratio. This arrangement is called Wheatstone's bridge, but not every Wheatstone's bridge you can ignore this. This Wheatstone's bridge is balanced, is said to be balanced if no current flows in that middle resistance R5 due to why? Delta V, potential difference, is 0 across it. And it happens, what happens? Balancing. It happens when a specific condition is met. And what is that condition? When R1 by R2 is equal to R3 by R4. Only when this condition is met, then the bridge is said to be balanced. Now this can be applied to even more extended Wheatstones also. For example, See, the ratio has to be same, only then you can ignore. So, say for example, or even for capacitors, say this is C, this is 3C, this is 2C, this is 6C, there is 4C in between. Guess what? This is also a Wheatstone's arrangement. Reason being, notice this capacitance by this capacitance, C by 3C, is 2C by 6C, 1:3 ratio. So definitely it is a balanced Wheatstone bridge. It is balanced. So which means we can ignore this, and the moment you ignore this, you just have these two, that's all. These two together, they are in series. So it will be how much? C3C by C plus 3C, that means 3C by 4. So this will become 3C divided by 4, this C and this 3C. I am using C1, C2 by C1 plus C2 formula because they are in series, so you have to use parallel formula, keep that in mind. Then these two capacitors, what is it? 2C and 6C. They are again in series, so use parallel formula. 2 6s by 2 plus 6, right? 2 into 6 divided by 2 plus 6, which is 12 by 8, which is nothing but divided by 4, which is 3 by 2. Okay, so 3C divided by 2. Okay, great. So now these two capacitors are obviously in parallel. So now just add them to get one single capacitance. That's the final answer. So C equivalent will be 3C by 4 plus 3C by 2. So it's as good as saying 3C by or 6C by 2 plus 3C by 2, taking common denominators. So that will become 9C by 2. That's the answer. Yeah. Just check it out. No, it's not 4 by 5, man. It's 9C by 2. Just check it out. 3C by 2 was different. 4 by 5, no. Cool, guys. C1, C2, yeah, divided by 4, yeah, 2 6 are 12 divided by 8, just 3 by 2, yeah, perfect. 3 by 2 plus 3 by 4, so multiplied. Oh, sorry, guys, what did I do? See, that is what happens after a long time. What did I do? Sorry, guys, this was 6C. 3C plus 6C divided by 4, 9C by 4, my bad. Something else I did. 9C by 4, my bad. Sorry, 9C by 4 is the answer. Yo, bro, I am teaching here for 5.5 hours. What else do you expect? I should be jumping like this with full excitement. Yeah, amazing, amazing. Now you can even extend it, like I said, for multiple arrangements like this. Say this is a resistor, this is a resistor, this is a resistor, 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 tung, 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 tung. R, 2R, 3R, 2R, 6R, oops, 2R, 4R, 6R, something, 3R, 6R, 9R, 4R, oh, it doesn't matter. This is also Wheatstone's, but this is extended. Can you see how? 1, 2, 3, 1, 2, 3, 1, 2, 3 ratio. Ratio is 1:2:3. Resistors are in that same ratio. That's it. So you can ignore whatever is there over here. Ignore. So then it becomes a much easier problem to solve, because now you have just 1, 2, 3 resistors in series, 1, 2, 3 resistor in series, 1, 2, 3 resistor in series, and their combination in parallel. So easily you can convert, into 3 parallel resistors and then convert it into one single resistor. Can you see that, everyone? So Wheatstones can be extended in multiple ways. in multiple different ways. Cool? Very nice. Amazing. In fact, Wheatstone's arrangement is also used to find unknown resistance at times. It's called as meter bridge. So, instrument called as meter bridge is exactly used to find an unknown resistance. So, what they do is use the exact concept of Wheatstone's bridge. So, you will put some, say, unknown resistance who I do not know what it is, and I will put some known resistance already in this particular part. This I don't know, this I know. What I will do to make a Wheatstone, I need two more resistances, but to get those resistances, I will use a wire who I know has a certain resistance per meter. So, using that wire, I can have different combinations of resistances. How? I'll tell you. Imagine this wire is there. Maybe it has 100 ohms. If I break it exactly in between, this will be 50. This will be 50. If I take that wire and break it somewhere at the quarter, this will be 25 ohms. This will be 75 ohms. If I break it at 1/10, this will be 10. This will be 90. So I can get different combinations of resistances by choosing a suitable point on that wire to be split. So that wire is called as the potentiometer wire or resistance wire. It has usually a length of 100 centimeters, usually, okay, but it can have even different lengths. And then what you do is basically connect these 2 points, connect these 2 points, and you power it up with some battery, of course. Kind of looking like meter's bridge, but not yet. So what you do, you take a small current measuring device, which is usually called as a galvanometer. It is a very sensitive device to current. And then you touch the other end of the galvanometer at different points. Different points on that wire. What you are doing when you tap it or touch it at different points? Say you are tapping it over here. This part has some resistance, this part has some resistance. Dividing this by this resistance, I get a ratio. If it happens to be exactly equal to this by this resistance, I am getting a kind of a Wheatstone arrangement which could be balanced or which may not be balanced. So if I have this resistance ratio X by R in this particular branch, somehow try to get a ratio exactly equal to X by R over here by tapping this galvanometer at different points, by moving it, by sliding it at different points. Somewhere or the other, this ratio will match. I don't know where. And wherever it matches, I stop over there. That is called as the balancing point. That is called as the balancing point, or sometimes also called as the null point. Why null point? Because exactly at that point, there is no current in the circuit. Galvanometer, my bad. Because you will see the Wheatstone will get balanced. It will become a balanced. It will become a balanced Wheatstone. It will become a balanced Wheatstone. Why? Is because this part has some resistance. This part has some another resistance. So maybe this by this resistance happen to be exactly equal to this by this resistance. If I call this resistance as R1, this as R2, so I can say this is equal to R1 by R2 at that null point. Null means 0, so current is 0, so this galvanometer is kind of useless at that moment. So it is perfectly balanced. So how do I know how much is R1 and R2? I know one thing. In a conductor, resistances are proportional to length. Resistances are proportional to length. So 100% this will be L1 by L2, meaning whatever is this length upon whatever is this length. But wait a minute, I already know what is L2 if I know L1. If this is L1, this is 100, this L2 will be 100 minus L1. That will be L2. So it will be L1 minus upon 100 minus L1. That's it. So that will be X by R. X is my unknown resistance. R is my known resistance. L1 becomes my balancing length, where the Wheatstones is balanced, so balancing length. 100 is the length of the wire, length of that potentiometer wire. So knowing all these quantities, easily you can find the unknown resistance, completely based on the Wheatstone's meter width. No, delta star method is not at all useful, man, for JEE. Don't waste your time on those phaltu waste methods. You will learn that in engineering. I have not seen any good use of it till now, and see, you can learn it for the sake of learning it, but it is of no use. Okay, you can most of the time solve the questions without a star or delta method, and very rare instances where it might be good, but for that one moment you want to learn that, I don't see any point. Cool. Now the last part, which is the power. So let's look at power. So electrical power. Okay, so this is the last part. Ready for it? Thank you, Samir, so much. Two things in electrical power. If there is a resistance through which some current is going, then you might see some energy loss which is happening. So there is some loss, or some heat which is being given up by that resistor, because the resistor sucks away that energy in a non-conservative manner, means it never gives it back. Once it is lost, it's gone forever. The second thing which we need to focus on is you have a cell of EMF E, and it is either giving that current or maybe it is taking in that current, like this. So this would be the case of discharging the cell when it supplies the current, and this would be the case of charging that particular cell. Okay. Now let's talk about this case first. When you have a current flowing inside the resistance, there is an energy loss which is being created. So that power which is lost is given by simply I squared into R. You can also write it as voltage across it, whatever is that voltage across that resistance. So V square by R, which is also current multiplied by resistance. All three things mean the exact same thing. In these cases, the battery is supplying power. So the power supplied by the cell, just like, oh sorry, I said IR, so sorry guys, it is not IR, it is voltage into current, my bad. Just like voltage into current formula is there, here EMF into current will be there. EMF into current, instead of voltage, EMF will be there. Whereas in the charging scenario, power is not supplied, power is being consumed by the cell. Power is stored by the cell. That will be again voltage into current. So supplied means it is coming out, stored means it is coming inside that particular cell. Is that clear, everyone? So these three scenarios, if you understand, you can solve many questions. This is for batteries, this is obviously for resistors. These two things you should know. Let me give you a very cool example on this. Ready for it, guys? Yeah? Yeah, I know, good old memories, man. What to do, man? Situations change, things change. It's not like, you know, we don't expect such things, but it happens, and now we can't do anything about it, right? So it's over, it's done, fine, not an issue. let's focus on what we are doing over here at that moment. Cool. Yep. So let's see. Imagine this is some, I don't know, EMF E, and I'm going to show a very interesting thing. This is R, this is external resistance R, and like this. I know it's a very simple circuit, but I'm going to show it to you via energy concept. Now look at this same question, but with the perspective of energy in mind. This battery is going to supply some current like this, because there is current which is coming out of the battery. So I can say the power which has been supplied by the cell, it will be used up by these two people, is being used up in loss. It is lost in the internal resistance, and it is also lost in the load or external resistance. Correct? When you talk about cells or batteries, the power supplied formula is EMF multiplied by current. When you talk about losses in resistances, it is I squared R. So it will be I squared multiplied by R here, and over here it will be again I squared multiplied by R, V square by R, anything you can use, but I am using I squared R. And word is used, so and means addition. Notice what happens, I cancels, and you are getting E is equal to IR plus IR, that means I into R plus R, therefore I will be E divided by R plus R, which is what was actually expected, isn't it? Similarly, just imagine, we take the scenario of a battery with some internal resistance connected to some external power supply of V volts. This is positive, this is negative. Now, this is the situation of charging a battery. We had discussed this before. Now, imagine the current will go like this, it will go like this, it will come out like this. If you think from energy perspective, the power which has been supplied from the external source is entering inside the battery. So power is being stored inside the cell, but at the same time this resistance is there and it is causing a problem, and some of that energy is lost in that resistance. Can you see that? Isn't it? Yeah, perfect. So what is the power supplied by the source? So whenever we talk about cells, supplied is voltage into current, EMF into current, whatever it is. So here EMF is V, current is I, so it will be V multiplied by I is equal to, is going into, it is charging, it is storing. How much is the energy stored in the cell per unit time? It is E into I, plus, because and word is used. There is some energy which is lost inside that resistance, and that is lost at the rate of I squared into R. Very good. I gets cancelled, so V will be E plus IR. Don't you remember this? We had written this equation down, and I wrote it down directly without proof, and I told you can do it by multiple ways, whatever. But you know, I'm showing this to you with energy concept, without using Kirchhoff's laws also. So a lot of times energy principles are very quick, very natural, because energy conservation you have been doing from 11th standard work for energy chapter. So it feels very natural at times. Got it, everyone? Beautiful concept of using energy. Sometimes you might be told some numerical questions like a heater coil of 500 ohms is connected to 20 volts is 20 volts for 1 minute 40 seconds. How much heat is generated? How much heat is basically generated? This kind of question. Now, here, why will heat be generated? Let's understand. There is a heater coil. Heater coil has some resistance and some current will go. There is some voltage also across it. So, there will be some heat power loss which will be created. We all know that power loss is I squared R, but current is not mentioned. So, no issues. Voltage and resistance is mentioned. So, I can use V square by R formula. You can use any of these three formulas which I have mentioned before. V square bar, I squared R or VI, depending on the use case. What is given, what is not given, you choose. Okay, so I am using V square bar because V and R were given. No issues, guys. Now, here is the thing. Power is energy per unit time. So, it is loss heat which is generated per unit time. So, that is V square by R. So, the question is how much heat has been generated. So, that heat will be V squared by R multiplied by time. Now, this is standard. Just substitute. Voltage is 20. So, 20 square divided by resistance which is 500. Time. 1 minute is 60 seconds plus 40. So, 60 plus 40 which is basically 100 seconds. So, into 100. 0, 0, 0, 0 cancels. So, 20 square is 400 multiplied by 1 divided by 5. So, this is just going to be 80 what? Joules. 80 joules. That is the answer. Yeah. 80 joules is the final answer. Got it? Everyone? So, this is how you can solve those power related questions. Now, one last thing over here. Two things actually. Sometimes those bulb questions also will come where you might be given there is a bulb rated at, let's say, 200 volts, let's say 10 watts. If it is now connected to 100 volts, what is the power consumed by the bulb? This kind of question. Now, whenever you get bulb questions, keep one thing in mind. Bulb should be treated like a resistance, and this resistance remains same no matter what the voltage. Remains same no matter what the voltage. It's a resistance coil at the end of the day. That's all. So, whether it is 200 or 100, the resistance is going to remain the same. So, first step is always to figure out what the resistance is. So, from this, I know voltage and power. So, power is a V square divided by R. Therefore, R is V square by P, and this, my dear friend, is going to remain constant. This will not change. V square by P. Correct? R will go on the top, P will come below. This can't change, this ratio. So, whatever is the voltage before by the power is the final voltage square divided by the power. So, what is the initial voltage? 200. What is the initial power? 10. What is the final voltage? 100. What is the final power? That's what I want to know. So, great. So, P2 on the top, 200 goes below, 10 goes on the top. So, 10 on the top, 100 square by 200 square. 200 square below, 10 on the top, perfect, 100 square as it is. Okay, so this, my dear friend, is just 0, 0 cancel. So 1 by 2 whole square, which is 10 by 4, which is 2.5 watts. So the new power is just 2.5 watts. The moment you reduce the voltage to 100 volts, the power has also come down. It will glow less, it will become less bright. Brightness will reduce. Got it? Understood? Yeah. It's up to you. If you want part by part, then you can check part by part lectures. But at this point of time, going in one shot big marathons is better. if you can stay for that long, but if you can't, then you can watch a big session into parts, or if you find part by part lectures more fruitful, you can watch that. Anything is fine, man. Anything is fine. Now the last thing over here, you have a battery connected to some external resistance. Yes, there will be some current which will be flowing in the circuit. That current, I know, will be, what has happened? 1 second. It's acting very weird. Yes, still Dolia, what do you mean by circuit mein power wala question? Means, so this current will be E divided by R plus R, we know that. Now if I ask you what is the power in this load, so the power loss in the load resistance, so that power, my dear, will be current square multiplied by resistance. Current square is, my God, that entire thing. So it will be E square, R is as it is, R plus R whole square. Now, let's say I have been given a choice. Listen, you can change the internal resistance. It's up to you. You choose whatever you want. But make sure that this battery causes a lot of power to be lost or delivered in this load. So I want maximum power to be lost in the load. So for maximum power loss in the load by changing internal resistance R. What will I do? Power is dependent on internal resistance. It's a function of R. Think logically. Power, your power which is there, is a function of internal resistance. Isn't that right? So there will be a point when that power will be maximum. This is that maxima point, and at maxima point slope will be 0. That means dP by dr will be 0. Solve this via maxima minima. After solving that entire thing, guess what you will get? The internal resistance comes out as external resistance. That's it. So this is exactly the theorem or the law which is called maximum power transfer theorem, which says that when internal resistance is equal to the external resistance, then maximum power is lost in this external resistance. That's it. That is the criteria for maximum loss to happen. That's all. That's simple. Cool? Yeah? Very good. Amazing. Understood, my dear warriors? Pakka? What this is? Pakka? Yes? So, say for example, this is 10 volts. There is some internal resistance, maybe 2 ohms. There is 3 ohms. And this is X ohms. I want maximum power loss across X. I want maximum power loss across X ohms. How much is X? That is the question. How much is X? That's the question. How do we do it? Use the theorem. Use the theorem. So many people, what they will do, they will think, sir, this is our battery, no sir. So internal resistance should be external resistance. So the answer for this will be 2 ohms. Don't do this foolishness. See, internal resistance is just a concept, and when we show in the circuit, we can show it this side, wherever you show it's the same thing. In fact, we can gulp down some external resistance and think about it as internal. So, if I want maximum energy to be lost across this, why not treat this entire thing only as my battery, man? This entire thing only is my battery. And feel as if this entire thing is internal resistance. So, maximum energy will be lost over here. So, maximum energy will be lost in X. If X is equal to internal resistance, that means X should be equal to 5 ohms. So, if X is equal to 5 ohms, you will see max loss of power. Understood? Is that clear? Isn't it amazing? So, this is called maximum power transfer theorem. So, that was our last concept. So, we have literally done everything starting from all the current parameters: density, field, conductivity, resistivity, temperature dependence, Ohm's law, right? Then we went to series parallel combinations, infinite circuits, disguised manner, Wheatstone, symmetry questions, connection removal, cube 3D symmetry questions, Kirchhoff's laws, solving them, different concepts which we even applied in capacitors, meter bridge, power losses, heat generated, power transfer theorem, everything guys was done in this particular lecture. So it's a beautiful class for all the kids who want to completely study this chapter and kickstart their journey. Problem solving sessions we will do later on, and we'll scale up your level obviously. In time to time, it can't happen in one go. So all the best. See you. Keep yourself updated. Stay tuned on this channel because a lot of amazing things are going to happen. Capto is there. Captain Shreyas is always there for all of you. Stay motivated, stay focused, and sleep well. Stay safe. Take care. Bye bye. Have a great time, guys.